Hello there, and welcome to Secretum Histories, where curiosity slows its breathing and history is allowed to unfold at an unhurried pace. Tonight, we settle into something carved in stone, something heavy, precise, and quietly unsettling. The ancient Egyptians left behind monuments that dominate deserts and textbooks alike, but hidden within their weight and symmetry are details that continue to resist comfortable explanation. Not legends of magic, not stories of gods descending in chariots of fire, but measurable cuts in granite, tolerances that rival modern engineering, and stone surfaces that behave as though touched by tools that officially did not exist. Somewhere in the world, you are listening to this at a particular hour. Perhaps the room is dim, perhaps the day has already asked enough of you. There is a clock nearby, ticking in neat seconds, marking time with obedient certainty. And yet, thousands of years ago, people without digital displays or steel drills managed to create structures that still make modern engineers pause. It creates a quiet contrast. We measure time in milliseconds, yet we still struggle to replicate some of their results with the same consistency. If you find this exploration calming, intriguing, or simply a thoughtful way to end the day, a gentle like or subscription helps this corner of quiet history reach others who might appreciate it. It keeps the lights on here, metaphorically speaking, and allows more of these slow journeys into the past. Now let us begin, not with speculation, but with stone. Egyptian monuments are not mysterious because they are large. Large things can be built with enough labour and time. What unsettles researchers are the details. Granite blocks weighing dozens of tons are fitted together with seams so tight that even a thin blade struggles to slide between them. Cylindrical drill cores extracted from ancient sites show spiral grooves that appear remarkably consistent. Stone vases carved from solid rock display walls so thin and symmetrical that modern craftsmen using powered lathes have difficulty achieving the same balance. These are not impressions formed by imagination. They are physical artifacts that can be measured, photographed, scanned, and tested. For generations, the standard explanation has rested on copper tools, stone pounders, wooden sledges, and patient labour. The Egyptians, we are told, possessed remarkable organisation and an abundance of manpower. They quarried limestone and granite, transported blocks across sand using sledges lubricated with water, and shaped them with copper chisels hardened by repeated hammering. It is a narrative that emphasises human ingenuity and persistence. There is no doubt that the ancient Egyptians were skilled builders. Their achievements in architecture, logistics, and social organisation were extraordinary. To replicate precise granite cuts using copper tools demonstrate that progress is possible, but extremely slow and often imprecise. When examining some ancient cores and drill holes, the striation marks suggest a steady feed rate that appears faster and more consistent than what hand-driven tools typically produce. These observations do not automatically imply advanced machines hidden beneath the sand. They simply create tension between expectation and evidence. When modern engineers study the internal chambers of the Great Pyramid, they notice flatness and alignment that approach modern standards of precision. The King's Chamber, constructed from massive granite blocks, shows surfaces that appear carefully levelled. The coffer inside that chamber is carved from a single block of granite and exhibits interior corners that are remarkably sharp and symmetrical. Transporting granite from Aswan to Giza required moving stone over 800 kilometres along the Nile. That feat alone is impressive but understandable with river barges and coordinated labour. The greater puzzle lies in shaping the granite once it arrived. Granite contains quartz crystals, which are much harder than copper. To cut granite effectively, one would typically require tools embedded with harder materials, such as iron or diamond. Iron tools were not in widespread use during the Old Kingdom when the Great Pyramid was built. When archaeologists present experimental reconstructions, they often demonstrate that copper saws combined with sand as an abrasive can cut stone. Sand contains quartz grains, and when applied between a copper blade and granite, it becomes the cutting agent. This is true. The sand does the cutting, while the copper acts as a carrier. However, such processes tend to leave irregular patterns and require significant time. Some ancient drill cores show spiral grooves that suggest a uniform descent of the drill bit, as if a mechanical feed mechanism maintained steady pressure. Even if one assumes extraordinary patience and labour, there remains the question of consistency. Human-driven drilling typically produces variable pressure, slight deviations and uneven spacing. Yet certain artifacts show patterns that look systematic. Engineers analysing these grooves have noted that the pitch appears uniform, raising the possibility of rotational speeds and feed rates more controlled than simple manual twisting would produce. Then there are the vases. Pre-dynastic Egyptian stone vases, some dating back over 5,000 years, are carved from diorite, granite, and other hard stones. Many are perfectly symmetrical along a central axis. Their necks are narrow, yet their interiors are hollowed out deeply and evenly. Modern machinists attempting to recreate these forms often rely on computer-guided lathes to achieve similar balance. Achieving that precision by hand would require remarkable skill, and a method capable of maintaining rotational symmetry. One possibility is that the Egyptians employed a form of lathe powered by human or animal force. Evidence of simple lathes exists in ancient cultures for woodworking. Whether similar devices were adapted for stone remains debated. No complete stone lathe has been found in the archaeological record, but absence of preserved machinery does not necessarily equal absence of method. Wood decays, metal corrodes. What survives most reliably is stone itself. Precision also appears in alignment. The Great Pyramid is oriented to true north with astonishing accuracy. Its sides deviate only a tiny fraction of a degree from cardinal directions. Modern surveys confirm this alignment repeatedly. While ancient Egyptians were skilled astronomers and could determine cardinal points using stars, achieving such alignment over a massive base requires careful measurement and control during construction. The base of the Great Pyramid is level to within a few centimetres across more than 200 metres. Creating such a level platform would demand systematic surveying. Techniques using water-filled trenches to establish a level reference plane are plausible and often cited. The Egyptians certainly understood water and levelling. Still, when one considers the cumulative precision across so many aspects of the structure, the scale of coordination becomes increasingly impressive. The Serapeum at Saqqara introduces another layer. Massive granite boxes, some weighing over 70 tons, sit in underground chambers. Their lids alone can weigh 30 tons. The interior surfaces of these boxes are smooth and flat, with corners approaching right angles closely enough to invite measurement. Modern researchers placing straight edges along these surfaces have reported minimal deviation. Moving these boxes into underground tunnels would have required careful planning and substantial manpower. It is tempting to assume that any unexplained precision must imply lost machines or external intervention. That temptation should be resisted. History is filled with underestimations of ancient capability. However, dismissing all anomalies as exaggeration is equally unproductive. A balanced approach acknowledges both the ingenuity of ancient builders and the unresolved technical questions that remain. In recent decades, scanning technologies such as 3D laser mapping have allowed researchers to examine structures in unprecedented detail. Micro-variations in surface flatness, tool marks, and structural alignment can now be quantified. Some findings confirm impressive craftsmanship. Others complicate long-held assumptions about construction methods. When modern engineers replicate ancient techniques in controlled experiments, results vary. Some reconstructions demonstrate that copper tools and abrasives can indeed shape granite effectively, albeit slowly. Others argue that certain artifacts show characteristics more consistent with rotary cutting tools operating at higher speeds. The debate continues in academic journals and independent research circles alike. it is important to remember that technology does not always leave obvious traces. Consider how much of modern infrastructure would survive 5,000 years without maintenance. Plastics degrade, steel rusts, electronics corrode. If an ancient society developed specialized tools primarily composed of perishable materials or rare metals later recycled, the physical evidence might be scarce. There is also the possibility that we misunderstand the scale of time. Egyptian civilization did not emerge overnight. Techniques refined over centuries could produce results that appear astonishing when viewed in isolation. Trial and error, incremental improvement, and generational knowledge transfer create outcomes that feel sudden to modern observers but were gradual in reality. What remains undeniable is that certain Egyptian artifacts continue to invite scrutiny. Their precision is measurable. Their surfaces reflect intentional shaping beyond rough quarry work. Their alignment speaks of careful planning. Whether the explanation lies in underappreciated manual techniques, lost intermediate technologies, or a combination of both, the stone itself remains steady and unbothered by debate. In museums, these artifacts rest behind glass, quietly defying simplistic narratives. Visitors walk past them, often focused on scale or decoration, rarely on tolerances or feed rates. Yet engineers who lean closer sometimes notice something different. A groove that seems too regular, a surface too flat, a symmetry too exact. It is in these small details that the broader question forms, not dramatically, not urgently, but persistently. Ancient Egyptian technology, particularly in stoneworking, appears at times to operate at a level that challenges our assumptions about what was available during that era. The challenge does not require sensational conclusions. It simply asks for careful observation. As we move deeper into this exploration, the focus will narrow from general impressions to specific examples. We will examine the cuts themselves, the drill cores, the granite boxes, the alignment of pyramids, and the experimental attempts to replicate them. Each piece adds texture to the larger picture. For now, it is enough to sit with the contrast. Soft copper against hard granite, manual labour against millimetre precision, desert sand against mathematical alignment. These elements coexist in the archaeological record, inviting patient consideration. The desert remains quiet about its processes. Wind passes over stone without commentary. Yet within these monuments are marks that look intentional, deliberate, and in some cases mechanically consistent. Whether those marks represent misunderstood craftsmanship or something more complex, they deserve a closer look. And so, as the evening continues and the mind begins to slow, we turn our attention to one of the most discussed aspects of this puzzle, the cuts themselves, lines in stone that appear cleaner than copper should allow, surfaces that seem smoother than abrasion alone might produce, details that have led engineers to take out calipers and magnifying lenses, not in disbelief, but in careful curiosity, ready to examine what the stone quietly reveals. When modern engineers step into Egyptian stone chambers with calipers, straight edges and scanning devices, the reaction is often quieter than popular documentaries suggest. There is no dramatic music, no sudden declarations, just a slow narrowing of the eyes and a second measurement to confirm the first. The issue is not that ancient Egyptians cut stone. That part is well established. The issue is how cleanly some of those cuts appear, especially when compared to the tools we're told they used. Copper was the primary metal available during much of Egypt's Old Kingdom. It is soft. On the Mohs scale of hardness, copper ranks around 3. Granite, which was widely used in temples, sarcophagi and pyramid interiors, contains quartz crystals that rank around 7. In practical terms, this means quartz is more than twice as hard as copper. If you press copper directly against granite without an abrasive, the copper will deform long before the granite yields. The standard explanation relies on sand. Quartz-rich sand acts as the true cutting agent. A copper saw or drill serves as a carrier, holding the abrasive in place while pressure and motion grind away the stone. This technique is valid. Experiments have shown that with patience granite can indeed be cut using copper tools and sand. It is slow, labour-intensive work, but not impossible. The debate begins when the physical evidence is examined closely. At sites such as Giza and Saqqara, researchers have documented stone surfaces that appear remarkably flat and smooth. In certain cases, saw marks on granite blocks show long, straight grooves running across the stone. These grooves are consistent in width and depth over significant distances. That alone does not prove advanced machinery. A skilled workforce using guide rails could produce straight cuts. However, the uniformity invites closer scrutiny. In several drill cores recovered from ancient sites, spiral grooves wrap around the cylindrical surface. These cores were extracted during the creation of holes in stone, often using tubular drills. The grooves resemble the threading pattern produced when a rotating drill bit advances steadily into material. The pitch of these spirals appears relatively constant along the length of the core. When a human manually twists a drill using a bow mechanism, pressure and rotation tend to vary slightly. Muscles tire, grip shifts, rhythm changes. Yet some ancient cores show patterns that appear strikingly even, as though the drill descended at a controlled and consistent feed rate. This observation has led some engineers to suggest that the drills may have operated with more efficiency than typically assumed. Experimental archaeologists have attempted to recreate these cores using copper tubes and quartz sand. The results do produce spiral grooves. However, matching the tightness and regularity observed in certain ancient examples has proven challenging. Some reconstructions require substantial time investment and constant attention to maintain uniform pressure. Even then, minor irregularities tend to appear. There is also the matter of depth progression. In some cases, analysis of the groove spacing suggests a relatively rapid penetration rate through granite. If the groove pitch represents the vertical advancement per rotation, and if that advancement appears significant, then the implied cutting efficiency exceeds what some manual reconstructions achieve under controlled conditions. It is important not to exaggerate. Not every drill core displays extraordinary characteristics. Some show variability consistent with manual operation, but a subset has drawn particular attention precisely because of its apparent regularity. Beyond drill cores, saw marks on granite blocks also raise questions. At certain temple sites, large granite blocks show linear striations running parallel to each other, as if produced by a long saw blade moving steadily across the surface. The lines appear evenly spaced. In some areas, they extend across multiple feet of stone without noticeable deviation. To produce such cuts manually, workers would need to maintain even pressure and consistent abrasive distribution along the entire length of the blade. This is possible in principle, especially with teams operating a large saw. Yet when modern teams attempt similar tasks, maintaining perfectly uniform grooves over long distances requires careful coordination and often results in slight inconsistencies. One of the most discussed examples involves a granite block showing a deep saw cut that appears to penetrate several centimetres into the stone. The cut walls look straight and relatively smooth. Engineers analysing photographs have pointed out that the apparent precision suggests a tool with stable guidance. Skeptics of the advanced technology hypothesis argue that photographs can mislead. Lighting, angle, and erosion can create impressions of precision that do not withstand microscopic examination. They emphasise that many ancient surfaces are rough and irregular, consistent with hand methods. They also note that Egyptian builders had centuries to refine techniques and train skilled artisans. Both positions deserve consideration. Precision does not necessarily imply modern machinery. It may reflect systematic craftsmanship supported by highly organised labour. Ancient Egyptian society was capable of mobilising thousands of workers for state projects. With enough repetition, even simple tools can produce refined results. However, there is another layer to consider: consistency across artifacts. When examining certain stone sarcophagi, particularly those carved from granite, one finds interior surfaces that appear remarkably flat. Measurements taken by independent researchers have suggested deviations on the order of millimetres across lengths exceeding a metre. Achieving that flatness by hand grinding would require persistent measurement and correction. Modern machinists often rely on surface plates and precision instruments to achieve similar tolerances. Without steel straight edges or dial indicators, ancient craftsmen would have needed alternative methods to test flatness. It is possible they used straight wooden beams and sighting techniques. Water-filled channels could provide level references. The ingenuity of ancient engineers should not be underestimated. Yet the cumulative effect of these observations builds a quiet tension. Copper, even with sand, is an inefficient cutting interface. It wears down quickly. The abrasive does the work, but it also erodes the tool. To produce large volumes of precisely cut granite, workers would need a steady supply of copper implements and abrasives, along with considerable time. Some researchers have proposed that the Egyptians may have used harder stone tools in combination with abrasives. Dolerite pounders have been found in quarries, indicating that pounding was used to shape granite roughly before finishing. But pounding leaves distinctive marks. The smoother surfaces seen on certain finished artifacts appear to result from a different stage of processing. There is also the possibility that the copper used in ancient Egypt was harder than commonly assumed. Alloying copper with small amounts of arsenic can increase hardness. Archaeometallurgical studies have shown that arsenical copper was known in antiquity. Even so, it remains significantly softer than quartz. The question then becomes one of efficiency. Did the Egyptians simply invest extraordinary labour hours into grinding and polishing granite until the desired precision was achieved? Or were there mechanical advantages, perhaps simple but effective, that allowed them to apply pressure and rotation more consistently than we imagine? A simple mechanical feed system does not require electricity or advanced metallurgy. A weighted frame applying steady downward force could produce more consistent drilling than hand pressure alone. A guided saw frame could maintain linear alignment more effectively than freehand motion. If such devices existed primarily in wood, their remains would likely not survive thousands of years. In that sense, the absence of surviving machinery does not automatically invalidate the possibility of mechanical aids. Modern replication attempts provide valuable insight. In several experiments, researchers have successfully drilled granite using copper tubes, sand and bow drills. They documented the time required and the wear on tools. In some cases, hours of effort were needed to achieve relatively shallow penetration. Scaling that up to the depth observed in certain ancient holes suggests significant labour investment. Yet ancient Egypt was a civilization capable of sustained, organised labour over long periods. Monumental projects were not weekend endeavours. They spanned decades. Workers were housed, fed and coordinated. Within that framework, slow but steady progress becomes plausible. Still, certain data points remain intriguing. Measurements of groove pitch on some cores imply that the drill advanced deeper per rotation than expected from typical manual setups. If accurate, this would suggest either unusually efficient abrasive management or some method of increasing applied pressure. Engineers who have studied these artifacts sometimes stop short of dramatic conclusions. Instead, they acknowledge that while traditional explanations are plausible, they do not fully account for every observation. There is room for refinement in our understanding of ancient methods. It is also worth noting that Egyptian stonework evolved over time. Early dynastic artifacts sometimes display even more intricate craftsmanship than later periods. In some cases, pre-dynastic stone vessels exhibit exceptional symmetry and thin walls. The technical skill evident in those objects suggests a high level of specialization early in Egyptian history. Whether this reflects lost techniques, gradual decline, or simply shifts in artistic priorities remains debated. The precision problem then is not a single anomaly. It is a pattern of small details that, when viewed together, invite careful reconsideration of assumptions. Copper against granite, spiral grooves with steady pitch, long straight saw marks, flat interior surfaces within heavy stone boxes. None of these observations alone demands an extraordinary explanation, but collectively they encourage a closer look at the practical realities of ancient stoneworking. As modern scanning technologies continue to analyse these surfaces, more data becomes available. High-resolution 3D models allow researchers to quantify deviations in flatness and curvature. Microscopic analysis of tool marks can reveal the nature of abrasives used. Is the pattern consistent with quartz grains alone, or are there hints of other materials? So far, mainstream archaeology maintains that known tools and methods suffice. Many scholars argue that skepticism toward ancient capability reflects modern bias rather than genuine mystery. Others contend that certain aspects deserve more experimental investigation. The stone itself remains impartial. It does not argue. It simply preserves the record of contact between tool and surface, and as we move forward, from cuts and grooves to the broader geometry of monumental structures, the conversation expands. Precision in individual artefacts leads naturally to precision in entire buildings. The next layer of inquiry concerns not just how cleanly stone was cut, but how accurately entire structures were aligned and assembled, block by block, across distances that still impress surveyors today. Granite does not yield easily. Anyone who's handled it in a modern workshop knows this. It resists chisels. It dulls blades. It demands patience and the right materials. Quartz crystals embedded within its structure glint under light and grind against any softer metal that dares to press against them. In today's world, shaping granite efficiently typically involves hardened steel, diamond-tipped blades, or industrial abrasives. The friction produces heat. The sound is sharp and insistent. Even with modern machinery, it is not a gentle process. Now consider the official timeline. During the Old Kingdom of Egypt, when the Great Pyramid and many granite structures were constructed, the primary metal available for cutting tools was copper. Iron was not yet in widespread use. Steel was unknown. The idea that copper tools were responsible for shaping massive granite blocks weighing dozens of tons invites a practical question, not dramatic but technical. How did a soft metal shape a far harder stone with such confidence? The answer most often given is abrasion. Copper did not need to be harder than granite if sand performed the cutting. Quartz sand, plentiful along the Nile, could act as the abrasive between tool and stone. The copper blade would hold the sand in place while motion and pressure gradually wore the granite away. Over time, grooves would deepen, surfaces would smooth, edges would sharpen. This explanation is consistent with basic physics. Abrasive machining works because the abrasive particles are harder than the material being cut. The carrier metal merely positions the abrasive. In theory, granite can indeed be shaped this way, but granite is not uniform limestone. Limestone is relatively soft and forgiving. It can be cut with copper chisels and stone tools with moderate effort. Granite, by contrast, requires persistent abrasion. When shaping large blocks, the scale of effort increases dramatically. Removing small amounts of material is manageable. Removing significant volumes with precision is another matter. In Aswan, where much of Egypt's granite was quarried, large unfinished obelisks still lie partially attached to bedrock. Dolerite pounding stones have been found there, suggesting that workers used repeated impact to chip away granite. Dolerite is harder than granite and effective for rough shaping. The pounding method produces characteristic marks, shallow depressions and irregular surfaces. However, rough shaping is only the first stage. The interior of the king's chamber in the Great Pyramid, constructed from granite blocks transported from Aswan, displays relatively smooth surfaces and tight joints. Sarcophagi carved from granite show flat interior walls and crisp edges. The transition from rough pounding to refined shaping demands controlled material removal. One granite coffer inside the Great Pyramid is carved from a single block. Its interior cavity is rectangular, with relatively straight walls and corners. Measurements suggest that the internal dimensions are fairly consistent. To hollow out such a block using only pounding stones would be inefficient. A tubular drill or saw combined with abrasive seems more practical. Yet granite's hardness continues to complicate matters. Copper wears down quickly when subjected to quartz abrasion. Maintaining tool integrity requires frequent reshaping or replacement. For large-scale projects, this implies an organised supply chain of copper and labour dedicated to tool maintenance. Archaeological evidence confirms that Egypt had significant copper resources, particularly from the Sinai Peninsula. Mining operations were well established. Smelting techniques allowed for the production of copper tools in substantial quantities. The Egyptians were not technologically naive. They understood metallurgy within their material limits. Even so, when modern experimenters attempt to replicate granite shaping using copper tools and sand, they often report slow progress and significant tool wear. Producing deep, clean cuts demands hours of sustained effort. The practicality of scaling such methods to thousands of granite blocks becomes a logistical consideration. Supporters of the traditional model argue that time was abundant. Monumental projects extended over decades. A workforce of thousands could devote cumulative labour hours that dwarf modern experimental setups. When multiplied across teams, slow processes become feasible. This is a reasonable point. Ancient Egypt operated on different timescales. Efficiency was not measured by quarterly reports but by dynastic ambition. If a pyramid required decades of incremental shaping, that timeline was acceptable. Still, hardness imposes physical constraints. Copper deforms under pressure. If too much force is applied, the tool bends or flattens. Maintaining consistent cutting depth in granite using a soft metal carrier requires careful management of pressure and abrasive distribution. Uneven pressure can cause wobbling or deviation. Some granite drill cores discovered at Giza show narrow cylindrical shapes with smooth outer surfaces. Spiral grooves wrap around them, as discussed previously. The tightness of these grooves has led to estimates suggesting substantial downward advancement per rotation. If those estimates are accurate, the implied efficiency appears higher than what some manual replications achieve. There is debate about measurement interpretation. Photographs can distort scale. Without precise metrology, conclusions about feed rates remain tentative. Nevertheless, the data continues to attract engineering interest. Beyond drill cores, consider the surface finish on certain granite artifacts. Polished granite reflects light smoothly. Achieving such polish requires progressive grinding with finer abrasives. The Egyptians clearly mastered polishing techniques. Statues carved from granite exhibit smooth, reflective surfaces that testify to patient craftsmanship. The existence of polished granite itself is not controversial. The question lies in intermediate stages, cutting large volumes accurately before polishing begins. Granite boxes in the Serapeum at Saqqara present another example. These massive containers, carved from single granite blocks, have interior walls that appear flat and parallel. The lids sit with close contact on the base. Modern researchers who have placed straight edges along some surfaces report minimal deviation. If these observations are accurate, achieving such flatness in granite would require systematic measurement. Flatness is not an automatic outcome of abrasion. It must be tested and corrected repeatedly. Modern machinists rely on precision surface plates and bluing techniques to identify high spots. Ancient craftsmen would have needed alternative methods. Perhaps they used flat reference stones to check surfaces against each other. By rubbing two surfaces together with abrasive between them, high spots can be worn down progressively, leading to mutual flatness. This lapping technique does not require advanced metals, only patience and understanding of geometry. Such possibilities demonstrate that hardness alone does not make precision impossible. It simply makes it demanding. Still, certain features remain intriguing. features. In some cases, granite blocks appear cut with long, straight channels that show little deviation over significant lengths. Producing such channels by hand with a copper saw and sand would require stable guidance systems. Without rails or frames, maintaining straightness becomes difficult. Wooden frames could have provided guidance. Weighted systems could have applied steady force. None of these require advanced industrial components. Yet the absence of preserved examples leaves room for speculation. There is also the matter of internal corners. In some granite coffers, interior corners approach relatively sharp right angles. Copper tools combined with abrasive would naturally produce slightly rounded corners due to tool shape and abrasive distribution. Achieving sharper transitions demands careful technique. Modern engineers studying these corners have sometimes remarked on their neatness. Critics respond that erosion and lighting can exaggerate apparent sharpness. High-resolution 3D scanning continues to refine these assessments. Granite hardness also influences tool mark patterns. Under magnification, the interaction between abrasive grains and stone leaves characteristic scratches. Detailed microscopic analysis can reveal whether those scratches align with quartz sand abrasion or suggest alternative cutting mechanisms. So far, mainstream analyses support quartz abrasion as the primary method. No conclusive evidence of steel or diamond tools has been found in Old Kingdom contexts. However, absence of evidence remains a complex matter when dealing with perishable materials and recycling practices. It is worth remembering that ancient Egyptians recycled metals extensively. Copper was valuable. Worn tools would be melted down and reforged. Any specialized components would likely have been reclaimed. Stone remains, metal disappears. The hardness problem therefore sits at an intersection of physics and logistics. Granite is hard, copper is soft. Abrasive methods bridge the gap. But the scale and precision of certain artifacts raise questions about efficiency and control. This does not require invoking lost civilizations or advanced outsiders. It simply acknowledges that ancient Egyptian stoneworking may have involved more sophisticated mechanical arrangements than are often illustrated in textbooks. A civilization capable of organizing pyramid construction could also design effective tool rigs. As we consider the hardness of granite and the softness of copper, the broader theme becomes one of capability versus assumption. It is easy to imagine ancient workers with primitive tools struggling slowly under the sun. It is more difficult to picture them devising clever mechanical aids that leave little trace. Yet history repeatedly shows that ingenuity flourishes within material limits. Ancient engineers built irrigation systems, aligned temples with stars, and constructed massive structures with remarkable coordination. The hardness of granite would not have discouraged them. It would have challenged them. The lingering question is not whether granite could be shaped with copper and sand. It clearly could. The question is whether the degree of precision observed in certain artifacts suggests methods more refined than commonly depicted. As the investigation continues, attention shifts naturally from individual tools to entire structures. Cutting granite is one step. Assembling massive granite blocks into geometrically precise chambers is another. The precision problem extends beyond hardness into alignment, symmetry, and spatial coherence on a monumental scale. And it is there, in the geometry of entire pyramids and the orientation of their sides against true north, that the conversation moves next, from the resistance of stone under tool to the deliberate placement of stone within space, measured not only by hardness, but by angle and direction across the desert plateau. Granite challenges the tool, geometry challenges the mind. When attention shifts from the surface of a single block to the outline of an entire monument, the scale of precision becomes harder to dismiss as incidental. The Great Pyramid of Giza is not only large, it is measured. At first glance, it appears as a simple, four-sided structure rising from the plateau. Time has stripped away much of its outer casing stones, leaving a stepped core exposed to wind and tourists alike. Yet beneath the weathered exterior lies a design that continues to surprise surveyors armed with modern instruments. The base of the Great Pyramid forms a square, each side originally measured approximately 230 metres. The difference in length between the longest and shortest side is minimal, measured in centimetres rather than metres. When expressed as a percentage of total length, the deviation is remarkably small. Achieving such uniformity over such a vast footprint requires more than rough estimation. The pyramid's orientation to the cardinal directions is even more striking. Its sides align with true north, south, east and west with astonishing accuracy. Modern measurements suggest an error of only a few arc minutes. In practical terms, this means the deviation from perfect cardinal alignment is tiny, even by contemporary construction standards. This alignment was achieved without compasses in their modern magnetic form. The Egyptians likely relied on astronomical observations. By tracking circumpolar stars and observing their transit across the sky, they could establish a true north reference line. Techniques such as the simultaneous transit method, involving the observation of two stars crossing the meridian at the same time, have been proposed as plausible methods. Such astronomical skill is impressive but not beyond the capability of ancient observers. Egyptian priests and astronomers monitored the heavens carefully. Their calendar depended on the heliacal rising of Sirius. Aligning a structure to the stars would have been consistent with their worldview and practical knowledge. However, astronomical alignment alone does not guarantee geometric perfection on the ground. Once a north reference line is established, it must be transferred across hundreds of metres accurately. Surveying over such distances requires careful levelling, measurement and verification. The base of the Great Pyramid was prepared by levelling the bedrock. Evidence suggests that trenches were cut into the bedrock and possibly filled with water to establish a level plane. Water naturally seeks its own level, making it a reliable reference. By marking the waterline around the perimeter, builders could determine where to remove high spots. Modern surveys indicate that the base is level to within a few centimetres across its entire span. Considering the size of the structure, this is a remarkable achievement. It suggests not only knowledge of levelling techniques but disciplined execution. Then there is the matter of corner accuracy. A square requires right angles. Establishing a precise right angle without modern protractors demands geometric understanding. The ancient Egyptians were familiar with basic geometry. Rope stretchers, known from historical records, likely used knotted cords to form triangles. A 3-4-5 triangle, based on the Pythagorean relationship, produces a right angle. Whether they formalised the theorem in the way later Greek mathematicians did is irrelevant. The practical knowledge of creating right angles was present. Applying such techniques over short distances is straightforward. Extending them across a 230-metre side while maintaining minimal cumulative error is far more challenging. Small inaccuracies compound. A slight deviation at one corner can magnify along the length of the base. The pyramid's sides not only align closely with cardinal directions, but their slopes appear consistent. The angle of inclination, approximately 51.5 degrees, produces a specific geometric relationship between base and height. Some researchers have noted that the pyramid's proportions approximate certain mathematical constants when expressed as ratios. Whether this was intentional design or coincidence remains debated. It is important to avoid retrofitting modern mathematical symbolism onto ancient structures. The Egyptians did not leave behind inscriptions explicitly stating that they encoded advanced constants within the pyramid's geometry. Yet the measurable ratios invite curiosity. Beyond external geometry, internal alignment introduces further complexity. The ascending passage, descending passage, and internal chambers follow specific orientations. The so-called king's chamber is positioned within the structure at a precise height relative to the base. The relieving chambers above it are carefully stacked to redistribute weight. The interior passages are not randomly placed. They reflect intentional planning within a three-dimensional framework. translating a geometric design from concept to execution. Inside millions of tons of stone requires coordination. One feature that continues to intrigue researchers is the slight concavity observed on each face of the pyramid. When viewed from above under specific lighting conditions, each face appears subtly indented along its centre line, creating an 8-sided appearance. This concavity is slight but measurable. The reasons for it are not definitively known. Some suggest it improves structural stability. Others believe it may have had symbolic or aesthetic significance. The precision of stone placement also contributes to overall symmetry. Although much of the outer casing has been removed, surviving casing stones show finely dressed surfaces. The joints between some casing stones are tight enough that inserting a thin blade is difficult. Achieving such close contact across numerous blocks would have required careful dressing and fitting. When blocks are fitted tightly, they distribute load more evenly. Precision is not merely aesthetic, it is structural. The pyramid has stood for over 4,500 years, enduring earthquakes and environmental stress. Its survival speaks to effective engineering. Still, symmetry at this scale continues to provoke examination. Modern construction projects rely on advanced tools, laser levels, steel measuring tapes, and computer modelling. Ancient builders relied on sighting rods, ropes, plumb bobs, and astronomical observation. The tools differ, but the outcome in this case approaches similar levels of geometric control. Critics of mystery-based interpretations argue that the Great Pyramid's precision is sometimes overstated. They point out that cumulative deviations do exist. The pyramid is not mathematically perfect. It exhibits small asymmetries and construction irregularities. Blocks vary in size. Internal passageways deviate slightly from straight lines. These imperfections matter because they demonstrate human involvement. The structure is not machine perfect. It reflects labour, correction, and adaptation. That nuance is important. It prevents the discussion from drifting into exaggerated claims. Yet acknowledging minor imperfections does not diminish the broader accomplishment. Building a structure of this scale with such consistent geometry remains extraordinary. There is also the question of replication. Modern engineers, if stripped of electricity and steel, could likely reproduce similar geometry using ancient techniques, given sufficient time and labour. The principles of surveying and levelling are not inherently modern. They rely on fundamental observations about light, gravity and measurement. What distinguishes the Great Pyramid is not that it violates physics. It is that it demonstrates a level of applied geometry and coordination that challenges simplistic narratives about ancient capability. In recent years, technologies such as muon tomography and high-resolution scanning have revealed previously unknown voids within the pyramid. These discoveries show that even now the internal architecture is not fully understood. The structure continues to yield information gradually. Symmetry also carries symbolic weight. In Egyptian cosmology, order, known as Mayat, represented harmony, balance, and cosmic stability. A pyramid aligned with cardinal directions may have embodied this principle physically. Precision could have been not only practical but philosophical. However, symbolism does not reduce the technical demands of execution. Aligning 4 massive sides to cardinal points with minimal deviation requires methodical verification. Every stage of construction must reference the original alignment. As courses of stone rise, alignment must be checked and corrected continuously. Even slight errors in lower courses would propagate upward. The fact that the pyramid maintains consistent orientation through its height suggests disciplined oversight. It is also worth noting that the Great Pyramid stands within a broader architectural context. Nearby pyramids at Giza show high degrees of alignment as well, though not always matching the same level of precision. This indicates that the knowledge required was not a singular anomaly but part of a broader tradition. The question then becomes not whether the Egyptians could achieve symmetry, but how they maintained it across such massive projects without leaving behind detailed technical manuals. Most Egyptian records focus on religious texts, administrative matters, and royal achievements. Detailed engineering treatises have not survived. This absence leaves room for speculation, but does not negate capability. The precision of the Great Pyramid, when viewed holistically, reflects mastery of surveying, levelling, and geometric planning. It challenges modern observers because it contradicts the assumption that advanced geometry requires advanced metal tools. Yet geometry itself is abstract. It requires understanding, not steel. A rope and stakes can produce straight lines and right angles. The sky can provide north. Water can establish level. The question is one of execution, scale, and persistence. As attention gradually shifts from the pyramid's external form to the methods by which its blocks were shaped and transported into position, symmetry becomes part of a larger technical mosaic. Precision in alignment complements precision in stoneworking. Both converge in the same monument, and as we continue to examine the physical traces left in stone, drill holes, saw marks, polished surfaces, the interplay between geometry and material returns to the forefront. The pyramid's shape may be symmetric, but the means by which that symmetry was achieved remain part of the ongoing discussion, drawing us deeper into the quieter evidence etched into granite itself. Among the most discussed pieces of physical evidence in ancient Egyptian stonework are not pyramids or statues, but cylinders. Modest in size compared to monumental architecture, these granite drill cores have drawn disproportionate attention because they preserve something intimate, the direct record of tool-meeting stone. A drill core is created when a tubular drill cuts a circular channel into stone. Instead of pulverizing the entire area, the drill removes a ring of material, leaving a solid cylinder in the center. Once deep enough, that cylinder can be extracted. The process is efficient for creating holes in hard materials. It reduces the amount of material that must be abraded. Several such cores have been recovered from sites around Giza and Saqqara. At first glance, they appear unremarkable. Cylindrical pieces of granite, often stored in museum collections or archives. But under closer inspection, their surfaces reveal a pattern that has become central to debates about ancient Egyptian technology. Spiral grooves wrapping consistently around the core. These grooves resemble threading on a screw. Each rotation of the drill appears to have advanced the tool downward slightly, creating a helical pattern along the outer surface of the core. The pitch of these spirals, the vertical distance between successive grooves, can be measured. Some engineers who have studied these cores have noted that the groove spacing suggests a relatively steady feed rate. If a drill rotates and simultaneously descends into material at a uniform rate, it leaves a spiral trace with consistent pitch. In modern machining, such patterns are expected when feed and rotation are mechanically regulated. The question arises when considering how such regulation would have been achieved in the Old Kingdom. The commonly accepted reconstruction involves a bow drill. A bow drill consists of a shaft attached to a cord that wraps around it. Moving the bow back and forth rotates the shaft alternately in clockwise and counterclockwise directions. A weight or hand pressure applies downward force. Sand is introduced between the drill edge and the stone to serve as abrasive. This system is simple and effective. It can produce circular holes. It can generate spiral grooves, especially if pressure and rotation are relatively consistent. However, manual operation introduces variability. The speed of rotation changes slightly with each stroke. Downward pressure fluctuates. Maintaining perfectly even advancement requires careful control. Experimental archaeologists have successfully drilled granite using copper tubes and sand. They have produced cores with spiral markings. In many cases, the resulting grooves display irregularities in spacing, reflecting natural variations in manual operation. Yet certain ancient cores appear to show grooves with relatively uniform spacing along significant portions of their length. Measurements published by some researchers have suggested advancement rates per rotation that seem comparatively high. If those measurements are accurate, the implication is that the drill penetrated granite more quickly than some experimental setups achieve. That observation does not immediately imply advanced machinery. It could reflect differences in abrasive quality, tool design, or operator skill. It might also reflect measurement interpretation. It is important to approach this evidence with caution. Photographs can exaggerate regularity. Erosion over millennia may alter surface appearance. Precise metrological studies are required to confirm groove pitch and depth accurately. Nevertheless, the presence of clear spiral patterns is not disputed. The mechanism that produced them remains the focal point. A tubular drill would have been necessary to create these cores. Copper tubes have been found in ancient Egyptian contexts. They could have been used in combination with sand to grind circular channels into granite. If a copper tube is rotated while pressed against abrasive-laden stone, the quartz grains between tube and granite perform the cutting. The key variables are rotation speed, downward force, and abrasive replenishment. A heavier weight applied steadily from above could produce more consistent downward pressure than hand force alone. If a frame held the drill vertically, it could reduce wobble and maintain alignment. Such a setup does not require advanced metallurgy. It requires mechanical ingenuity. A weighted frame constructed from wood could apply steady pressure. A flywheel effect could smooth rotational motion. Teams of workers could operate the system in coordinated rhythm. One proposal suggests that ancient builders may have used a simple mechanical feed system, possibly involving weights that gradually lowered the drill as material was removed. If so, the spiral groove would reflect the controlled descent of the tool. Critics of this interpretation argue that no clear archaeological evidence of such feed mechanisms has been found. Wooden frames, if used, would likely have decayed. Metal components would have been recycled. The absence of preserved machinery leaves interpretation open. There is also the matter of groove depth. Some cores show relatively deep grooves, implying significant penetration per rotation. If accurate, this would suggest either very effective abrasive action, or a tool material capable of resisting wear better than pure copper. Archaeometallurgical studies indicate that some ancient Egyptian copper tools contain small amounts of arsenic, increasing hardness slightly. Even so, arsenical copper remains softer than quartz. It would still rely heavily on abrasive action. Another factor to consider is abrasive selection. Not all sand is identical. The Nile sands contain quartz, but grain size and purity vary. A well-selected abrasive mixture could increase efficiency. Workers may have understood empirically which sands cut best. The geometry of the drill tube itself also matters. A thicker wall might distribute pressure differently. A slightly tapered edge could concentrate force. Even minor design variations influence performance. When modern engineers analyse the cores, they often compare groove pitch to expected feed rates from manual bow drilling. Some conclude that the advancement appears too rapid. Others argue that under optimal conditions, similar results are achievable. It is also possible that ancient drill operators developed a rhythm and technique refined over years of practice. Repetition breeds consistency. Skilled artisans can produce surprisingly uniform results even with simple tools. Beyond efficiency, there is the question of concentricity. Some cores appear relatively cylindrical and centered within their original holes. Achieving concentric drilling requires stabilizing the tool to prevent lateral drift. A guiding collar or frame could assist in maintaining verticality. The holes from which these cores were extracted also display circular geometry. Some are deep relative to their diameter. Maintaining straight alignment over depth requires careful control. One must avoid romanticizing the mystery. There is no need to invoke lost civilizations or exotic technologies. The evidence points to sophisticated stoneworking within the material constraints of the era. The debate concerns degree of sophistication, not impossibility. What makes the drill cores compelling is that they preserve dynamic information. Unlike a finished statue, which reflects final shaping, a core captures the motion of the tool itself. It is a fossilized record of rotation and descent. When viewed under magnification, the grooves trace a path through time. Each spiral represents rotation. Each increment downward represents pressure applied and abrasive renewed. Modern replication efforts continue. Researchers have experimented with varying abrasive mixtures, tube thicknesses and feed systems. Some results approach the groove regularity seen in ancient examples, others fall short. Variability in experimental outcomes keeps the discussion active. The broader context is essential. Drill cores are not isolated artifacts. They are part of a larger pattern of stoneworking that includes saw marks, polished surfaces, and tightly fitted blocks. The cumulative evidence suggests an advanced understanding of abrasion techniques. It is possible that ancient Egyptian workshops operated with more mechanical assistance than is often illustrated in simplified depictions. Ropes, weights, wooden frames, and coordinated labour can produce controlled motion. The mechanical advantage does not require electricity. The absence of surviving machines does not negate their former existence. Perishable materials rarely endure. What remains is the stone, bearing silent testimony to the method used. As attention gradually shifts from cylindrical holes to larger structural elements, the question broadens. If drilling granite required such precision and control, what of the massive stone boxes in underground chambers? What of the thin-walled vases carved from solid diorite? The spiral grooves, modest in size yet rich in implication, serve as a bridge. They connect the microscopic evidence of tool marks to the macroscopic reality of monumental construction. Each groove invites examination not because it defies physics, but because it hints at a disciplined technique that may not yet be fully understood. And as the exploration continues, the focus will move from rotating drills to enclosed chambers beneath the sands, where granite blocks weighing dozens of tons rest in darkness, their surfaces as measured and deliberate as the spirals etched into the cores that once emerged from living stone. Beneath the sands of Saqqara, away from the sunlight that washes over pyramids and open courtyards, there is a network of underground galleries cut into bedrock. The air is cooler there, the ceilings are lower, the walls are narrow corridors carved through limestone, and within these chambers rest objects that shift the conversation from geometry and drill marks to something heavier, quieter, and more difficult to dismiss with simple explanations. The Serapeum of Saqqara houses a series of massive granite boxes, each one carved from a single block, each one paired with a lid that, on its own, weighs tens of tons. Estimates place some lids at around 30 tons, with the boxes themselves exceeding 60 or 70 tons in total mass. The numbers are not controversial. The stone is there. The weight can be calculated. Transporting granite of that size from Aswan to Saqqara required river barges, coordinated labour, and careful planning. That achievement alone demonstrates remarkable logistical capability. But once the blocks arrived and were lowered into subterranean galleries, the shaping and fitting of these boxes present a different kind of puzzle. The interior surfaces of several Serapeum boxes appear strikingly flat. Researchers who have placed straight edges along the inner walls have reported minimal deviation over lengths exceeding a metre. The corners approach right angles closely enough to draw comment from modern machinists accustomed to working with surface plates and precision instruments. Flatness is not accidental. It does not emerge naturally from rough shaping. To achieve flatness across a large granite surface, one must remove high spots systematically. The process involves repeated testing and correction. In modern workshops, machinists use surface plates coated with marking dye to reveal unevenness. Ancient craftsmen would have needed alternative methods. One plausible technique involves lapping. If two surfaces are rubbed together with abrasive between them, high points wear down progressively, resulting in mutual flatness. This process does not require advanced metal tools. It requires time, abrasive material, and an understanding that surfaces can be corrected through iterative contact. However, lapping large granite surfaces inside a confined underground space while maintaining squareness between walls introduces practical challenges. Each interior wall must not only be flat, but also perpendicular to adjacent walls. Achieving consistent right angles without modern squares demands geometric discipline. The lids present another layer of interest. Some appear to sit atop the boxes with close contact. Observers have reported that inserting a thin blade between lid and box is difficult in certain areas. If accurate, this suggests careful dressing of both mating surfaces. A lid weighing 30 tons does not gently settle into place. Lowering it onto a box requires controlled movement. If the fit is too tight in one area, the stone could chip or bind. Achieving uniform contact implies forethought and testing prior to final placement. Skeptics of exaggerated claims argue that not all boxes in the Serapeum display extraordinary precision. Some surfaces are rougher, some corners less exact. It is important to acknowledge variation. The site contains multiple boxes spanning different periods. Craftsmanship may have evolved or fluctuated, yet even accounting for variation, the overall quality of certain boxes invites technical curiosity. Granite, as previously discussed, is hard and resistant. Shaping its interior surfaces requires effective abrasive management. One must also consider the spatial constraints. These boxes are located within underground galleries carved into limestone bedrock. Transporting multi-ton granite blocks into these corridors would have required careful planning. It is unlikely that boxes were fully shaped before placement if shaping required open-air access. Alternatively, shaping could have occurred before transport, necessitating protection during movement. The interior volumes of the boxes are substantial. Hollowing out such volumes from a solid granite block requires removing large amounts of material. Tubular drills and saws could have been used in combination with pounding and abrasion. The process would have generated granite dust and debris. Managing this within confined spaces adds complexity. Measurements reported by some independent researchers suggest that the internal dimensions of certain boxes vary only by small margins from one end to the other. Maintaining consistent wall thickness across a multi-meter span in granite is demanding. It requires continuous measurement. Ancient Egyptians possessed measuring rods and plumb bobs. Wall paintings depict surveyors using cords and sighting tools. Their knowledge of basic geometry is well documented. None of these tools are inherently incapable of supporting precise work. The debate centres not on possibility, but on efficiency and scale. How much labour would have been required to produce multiple granite boxes of this size with such finish? Over what time frame? Under whose supervision? The Serapeum boxes are traditionally associated with the burial of sacred Apis bulls. Inscriptions indicate that these animals were mummified and placed within the granite containers. If their function was funerary, the emphasis on durability and solemnity makes sense. However, the sheer mass and finish of the boxes have led some to speculate about alternative purposes. It is important to separate evidence from imagination. There is no credible evidence that these boxes served as energy devices or contained advanced technology. The function appears ritual and funerary, yet ritual significance does not reduce technical interest. The Egyptians often invested immense resources into objects tied to religious belief. Precision and durability would have held symbolic weight. One of the most discussed aspects of the Serapeum boxes is the reported measurement of flatness using modern instruments. In some cases, laser scanning has been employed to map interior surfaces. Results vary depending on methodology and sample selection. Some surfaces show slight irregularities, others appear surprisingly consistent. It is essential to avoid cherry-picking. The Serapeum contains multiple boxes. Each must be evaluated individually. Generalizing from a single example risks distortion. Still, when modern machinists encounter granite surfaces that approach modern tolerances without evidence of steel or diamond tooling, they pause, not because they believe in lost civilizations, but because they recognize the labor implied. Transporting a 70-ton granite block is one challenge. Hollowing it out symmetrically is another. Ensuring that its lid aligns closely along its perimeter introduces a third. The underground environment also preserves surfaces differently than open-air monuments. Reduced exposure to wind and sand may have preserved sharper edges. What appears crisp today may reflect both original workmanship and environmental protection. Some researchers have suggested that the boxes could have been finished in open air before installation in the galleries. If so, precise shaping would have occurred with full access around the block. Lowering finished boxes into the underground chambers would then require ramps, rollers, and coordinated manpower. Engineering such movement without modern cranes is demanding but not implausible. Egyptians transported obelisks weighing hundreds of tons. Reliefs depict large statues moved on sledges lubricated with water. The logistical culture existed. The more subtle question concerns the measurement culture. Precision requires not only tools but values. A society that prioritizes symmetry and alignment invests in verification. In Egyptian cosmology, order was central. Maintaining Ma'at, the principle of balance and harmony, extended beyond ethics into architecture. Structures aligned with cosmic order reflected divine stability. In that context, precision would carry spiritual as well as practical significance. Nevertheless, granite does not yield simply because of belief. It responds to force and abrasion. Achieving millimetre-level alignment across multi-ton surfaces requires systematic correction. One plausible explanation is that ancient workshops operated with master craftsmen overseeing apprentices. Knowledge of flatness testing, squareness checking, and abrasive sequencing would have been transmitted orally and through practice. Over generations, techniques would refine. The absence of surviving instruction manuals leaves modern observers reconstructing methods from stone evidence alone. It is a form of reverse engineering across millennia. The Serapeum boxes, resting in darkness beneath Saqqara, embody this challenge. They are neither magical nor inexplicable. They are physical artifacts shaped by human hands. Yet the degree of control visible on certain surfaces encourages continued examination. As attention gradually shifts from underground chambers back toward open-air artifacts, another category of objects presents its own version of precision. Small stone vases carved from hard materials with walls so thin and symmetrical that they seem almost delicate despite their durability. The scale changes from 70 tons to a few kilograms. But the underlying question persists. How did ancient craftsmen achieve such consistency in materials that resist simple shaping? And what does that consistency reveal about the techniques employed across different contexts within the same civilization? At the edge of the Giza Plateau, not far from the Great Pyramid, the Sphinx sits in a shallow depression carved directly from the limestone bedrock. It is not assembled block by block like the pyramids. It was carved in place, its body emerging from the living rock of the plateau. Over time, wind has moved across its surface. Sand has gathered and been cleared away again. Tourists have stood before it for generations, looking up at a face worn smooth by centuries of exposure. The Sphinx presents a different kind of puzzle, not about symmetry or drill marks, but about erosion. The weathering patterns on its body and the surrounding enclosure walls have become the centre of a debate that touches on geology, climate history and chronology. Limestone is softer than granite. It erodes more readily under environmental forces. Wind-carrying sand can abrade surfaces gradually. Water can dissolve and carve channels into stone. The type of erosion visible on a structure can reveal clues about the conditions it has endured. Most Egyptologists date the Sphinx to the reign of Pharaoh Khafre, around 2500 BCE, during the 4th dynasty. This places its construction roughly at the same time as the pyramids of Giza. The Sphinx is traditionally seen as part of Khafre's complex, possibly bearing his likeness. However, in the late 20th century, some researchers proposed that the erosion patterns on the Sphinx's enclosure walls are more consistent with prolonged water exposure than with wind-driven sand alone. They pointed to vertical undulating channels and rounded profiles in the limestone as evidence of rainfall erosion. The argument rests on geological interpretation. Wind erosion tends to produce horizontal abrasion patterns, particularly in desert environments where sand moves laterally. Rainfall erosion, by contrast, can create vertical streaking and rounded edges as water flows downward across surfaces. If the Sphinx enclosure exhibits significant vertical weathering consistent with heavy rainfall, then the monument might date to a period when Egypt experienced a wetter climate. Paleoclimatic data indicate that the Sahara was much wetter, thousands of years before the Fourth Dynasty. Periods of substantial rainfall occurred during the late Pleistocene and early Holocene. The implication of this argument is significant. If the Sphinx predates the Fourth Dynasty by thousands of years, then it would challenge conventional chronology. Mainstream Egyptologists and geologists have responded with alternative explanations. They note that limestone quality varies across the Sphinx and its enclosure. Some layers are softer and erode more rapidly than others. Differential weathering can produce rounded and vertical patterns without requiring prolonged heavy rainfall. Additionally, the Sphinx has undergone multiple phases of burial and exposure. Over centuries, sand covered much of its body, protecting some surfaces while leaving others exposed. Moisture from occasional rains, condensation and groundwater fluctuations could contribute to complex erosion patterns. Salt crystallization is another factor. When moisture penetrates porous limestone and later evaporates, salt crystals can form within the stone. The expansion of these crystals exerts pressure, causing flaking and surface degradation. This process can create irregular patterns that mimic water erosion. Geologists studying the site have examined the rock strata closely. Some argue that the vertical fissures in the enclosure walls align with natural fracture patterns in the limestone, amplified by weathering. The presence of these natural joints can guide erosion in specific directions. Furthermore, evidence of quarrying around the Sphinx indicates that the enclosure was cut as part of a coordinated construction effort. Blocks removed from the enclosure appear to have been used in nearby temples associated with Khafra's complex. This contextual linkage supports a Fourth Dynasty date. The debate remains active because both sides present data. Photographs of the enclosure walls show vertical channels that appear striking. Measurements of weathering depth vary. Climate reconstructions provide broader context but cannot pinpoint specific rainfall impacts on a single monument. There is also the matter of repair. The Sphinx has been restored multiple times throughout history. Ancient Egyptians themselves undertook restoration projects. Later rulers added blocks and repaired eroded sections. Modern conservation efforts have introduced additional materials. Distinguishing original weathering from later damage and restoration complicates analysis. Surfaces visible today may reflect cumulative effect across millennia. Some proponents of an earlier date argue that the body of the Sphinx shows more severe weathering than the head. They suggest that the head may have been recarved from an earlier larger head, possibly altering its proportions. If true, this could imply that the monument existed before its current facial form was shaped. Mainstream scholars counter that differences in weathering between head and body can be explained by variations in limestone quality and exposure. The head is carved from a harder layer of limestone than parts of the body. Harder stone resists erosion more effectively. The question is not simply whether water touched the Sphinx, it certainly did. Occasional rainfall and moisture have affected the plateau over thousands of years. The question concerns duration and intensity. Did the Sphinx endure sustained heavy rainfall over centuries? Or can its weathering be accounted for within the climatic fluctuations of the Old Kingdom and subsequent periods? Geological surveys have examined sediment deposits around the enclosure. Some studies suggest that patterns are consistent with intermittent rainfall rather than prolonged monsoon-like conditions. Others argue that certain erosion features imply greater water exposure. The broader context of the Giza Plateau is also relevant. If heavy rainfall significantly shaped the Sphinx enclosure, similar patterns might be expected on nearby structures of the same era. Yet the pyramids and associated temples do not display identical weathering features, though differences in construction material and exposure complicate direct comparison. it is important to avoid overstating the mystery. The Sphinx does not defy geology. It presents a case study in interpreting complex erosion over long time scales. The debate illustrates how a single monument can become a focal point for larger questions about chronology and climate. If the Sphinx were substantially older than the pyramids, it would reshape narratives about Egyptian civilization's development. Such a claim requires robust evidence. So far, the majority of Egyptologists maintain the 4th dynasty date, supported by archaeological context, tool marks, and associated structures. The weathering hypothesis remains a minority view within academic circles, though it continues to attract public attention. The Sphinx itself remains silent. Its face, worn yet composed, looks eastward. Its body bears the marks of time. Whether those marks reflect centuries of desert wind, episodic rain, groundwater action, or some combination of all three, they remind us that stone records environmental history as well as human intention. The erosion debate also underscores a broader theme running through this exploration. Physical evidence can be interpreted in multiple ways. Precision in stone cutting invites technical analysis. Weathering patterns invite geological interpretation. Each requires careful measurement and restraint. As the discussion shifts from erosion to craftsmanship once again, attention returns to objects less massive, but no less intriguing. In museums around the world, small stone vases carved from hard materials sit behind glass. Their walls are thin, their symmetry is precise, and they raise questions not about erosion, but about control at a scale measured in millimeters rather than meters. The contrast between the monumental Sphinx and a handheld granite vessel may seem large, yet both belong to the same civilization. Both reflect choices in stone, and both contribute to the ongoing effort to understand how ancient Egyptian technology balanced material limits with enduring results. In museum displays, often tucked behind glass in softly lit cases, there are objects that rarely receive the same attention as pyramids or colossal statues. They are small enough to fit in two hands. They do not dominate skylines. They do not weigh dozens of tons, and yet in some ways, they are more unsettling than any monument rising from the desert. These are the stone vases of ancient Egypt. Many of them date to the pre-dynastic period and the early dynasties, before the construction of the Great Pyramid. They are carved from hard stones, granite, diorite, basalt, schist. Some are symmetrical to a degree that invites careful measurement. Some have narrow necks leading to wide internal cavities. Some have walls so thin that light almost seems to pass through their edges. It's one thing to carve a rough container from limestone. It is another to hollow out a block of diorite, one of the hardest stones available in the region, and produce a vessel whose wall thickness remains consistent around its circumference. The challenge begins with the material. Diorite and granite are both harder than copper. Like granite blocks used in monuments, these stones require abrasive methods to shape. The smaller scale of the vases does not reduce the technical difficulty. In fact, it intensifies it. Precision increases as size decreases. If a massive granite block is slightly uneven by a few millimeters, the deviation may be difficult to notice without instruments. In a small vase with thin walls, a deviation of even a millimeter becomes obvious to the eye and hand. Many of these vases exhibit rotational symmetry. Their outer profiles curve smoothly around a central axis. Their bases are centered. Their necks align cleanly with the body. Some modern machinists who have examined 3D scans of these vessels have remarked that the symmetry approaches what one might expect from a lathe. The lathe is a simple but powerful tool. It rotates a workpiece around an axis while a cutting tool shapes its surface. Evidence exists for early lathes in ancient civilizations, primarily for woodworking. Rotating stone on a lathe presents additional challenges due to weight and hardness. There is no preserved stone lathe from ancient Egypt. There are no surviving diagrams of stone-turning workshops. Yet the geometry of some vases suggests rotational shaping rather than purely freehand carving. One plausible method involves mounting a rough stone blank between supports and rotating it using a cord or bow mechanism. Abrasive could be applied to shape the exterior. Such a process would naturally produce symmetry around the axis of rotation. Hollowing the interior, particularly through a narrow neck, introduces further complexity. Tubular drills could be used to remove a central core, similar to the granite cores discussed earlier. After drilling, abrasives attached to shaped tools could widen and smooth the interior. Maintaining consistent wall thickness would require frequent measurement. Ancient craftsmen likely relied on calipers, simple measuring tools with two arms used to compare distances. Calipers made of wood or metal could have been employed to check wall thickness at various points. Even with calipers, shaping hard stone to thin tolerances demands careful material removal. Removing too much material cannot be reversed. The artisan must proceed gradually, testing repeatedly. Some vases have wall thicknesses of just a few millimeters. In certain examples, the thinness remains relatively uniform around the body. This uniformity has led some observers to describe them as impossible, given the presumed tool set. The word impossible deserves caution. Nothing in physics prevents a skilled artisan from gradually abrading stone to thin dimensions. The question is how efficiently and consistently this could be achieved using copper tools and abrasives. Modern experiments attempting to replicate similar vessels have demonstrated that it is possible to carve stone vases with hand tools and abrasives. However, achieving the highest levels of symmetry and thinness often requires extended labour and meticulous control. One must also consider that these vases were prestige items. They were not everyday pottery equivalents. Their rarity suggests specialisation. Workshops dedicated to elite goods could invest extraordinary effort into individual pieces. Pre-dynastic Egypt was not technologically primitive in the simplistic sense. Even before the Old Kingdom, artisans displayed refined craftsmanship in stone, ivory and metal. The stone vase tradition appears early and flourishes during periods when large-scale monuments had not yet reached their peak. This chronological placement adds nuance. The highest quality stone vases are often older than the pyramids. If technological sophistication increased gradually over time, one might expect earlier artifacts to be cruder. Instead, some of the finest vases belong to earlier periods. There are possible explanations. Artistic styles evolve. Later periods may have favoured different aesthetics. Production techniques may have shifted. The apparent decline in certain stone vessel traditions does not necessarily indicate loss of capability. It may reflect changing priorities, yet the technical achievement remains. When examined with modern scanning tools, some vases show deviations in symmetry that are small but measurable. They are not mathematically perfect. Minor irregularities confirm hand involvement. The surfaces bear traces of abrasion and finishing. This is important. The vessels do not appear to be products of industrial machining in the modern sense. They retain subtle imperfections consistent with manual processes. The intrigue lies in the combination of thinness, symmetry and hard material. A narrow-necked vase carved from solid diorite requires the artisan to hollow out the interior through a restricted opening. The internal cavity must be shaped without direct visual access to the lower walls. Tools inserted through the neck would need to reach deep while maintaining controlled contact with the interior surface. This suggests the use of shaped abrasives attached to rods or rotating mechanisms. It also implies a strong spatial understanding of interior geometry. Some researchers have proposed that ancient craftsmen may have used a form of core drilling combined with interior lapping to refine the shape. Others suggest a rotational system where the vase blank was spun, while abrasive tools shaped both interior and exterior. If rotational methods were used, they may not have resembled modern metal lathes. A simple horizontal spindle supported by wooden frames could suffice. Rope-driven rotation, combined with steady hand-applied abrasives, could generate symmetry. Again, the absence of preserved machinery complicates conformation. Wood decays, rope rots, metal is recycled, stone remains. The vases sitting quietly in museum cases carry no inscriptions explaining their manufacture. They offer no diagrams of workshops. They simply exist as finished objects. Some of the most symmetrical examples have been subjected to digital scanning and computational analysis. These studies reveal that while the symmetry is high, it is not absolute. Variations of a fraction of a millimetre exist. This supports the idea of skilled manual work rather than automated machining. Nevertheless, the degree of precision challenges simplistic depictions of ancient artisans as working only with crude implements. It is possible that stoneworking techniques were more advanced and specialised than commonly portrayed. Workshops may have developed methods refined over generations, guarded as trade secrets within artisan families. The social structure of ancient Egypt supported craft specialisation. Artisans working for elite patrons could dedicate their careers to mastering specific materials. The vases also reflect aesthetic discipline. Their forms are balanced, their proportions deliberate. Precision here serves beauty as much as function. What makes them compelling in the context of unexplained technology is not that they violate known principles, but that they compress technical achievement into small objects. A 70-ton granite box impresses through mass. A thin-walled diorite vase impresses through control. Together they paint a picture of a civilization comfortable shaping hard stone with confidence. As attention moves from handheld vessels back to the broader landscape of the Giza Plateau, the question expands again. If artisans could achieve such thinness and symmetry on small objects, what tools and techniques were available when shaping massive architectural elements? How did precision scale from centimetres to hundreds of metres? The small and the large are connected. The same understanding of material, measurement and geometry underlies both, and as the exploration continues, focus will shift outward once more, from objects that fit in the palm of a hand to the entire plateau itself, where stone, layout and alignment suggest a landscape engineered with intent rather than assembled by chance. From a distance, the Giza Plateau appears as a collection of monuments placed upon a desert shelf overlooking the Nile Valley. 3 large pyramids, smaller subsidiary pyramids, causeways, temples, the Sphinx, and scattered mastabas stretch across the limestone bedrock. To many visitors, it looks like an ancient cemetery expanded over time, structures added where space allowed. But when examined more closely, the arrangement begins to feel less like decoration scattered across terrain and more like a coordinated plan imposed upon it. The plateau itself is not flat by default. It consists of layered limestone rising above the surrounding floodplain. Builders did not simply place pyramids on untouched sand. They cut into bedrock, levelled large areas, carved trenches, and integrated existing geological features into their designs. The Great Pyramid does not sit on an artificial foundation built upward. Its base is partially carved into the natural rock. Builders removed higher sections of limestone to create a level platform. In some areas, the bedrock remains visible beneath the lowest courses of stone. This integration of structure and terrain suggests careful surveying before construction began. The second pyramid, traditionally attributed to Khafra, appears slightly taller than the Great Pyramid from certain vantage points, despite being marginally smaller. This is due to its placement on slightly higher ground. Whether intentional or incidental, the effect contributes to a balanced visual composition across the plateau. The third pyramid, smaller yet proportionally consistent, occupies a lower position but maintains alignment with the others. The 3 pyramids form a diagonal line when viewed from above, oriented roughly southwest to northeast. The relationship between their placement and nearby temples and causeways indicates planning rather than random positioning. Causeways connect pyramids to valley temples closer to the Nile floodplain. These causeways run in relatively straight lines across the terrain, cutting through rock and aligning with cardinal directions or specific angles. The consistency of these alignments suggests that builders conceived the layout as an interconnected system. The Sphinx, carved from bedrock near the Valley Temple of Khafre, occupies a position that complements the larger architectural scheme. Its orientation due east aligns with the rising sun at the equinox. Whether this alignment was intentional or a product of practical considerations remains debated, but the consistency across the plateau reinforces the sense of coordinated design. When aerial imagery and satellite data are analysed, patterns become more apparent. The pyramid's bases align closely with cardinal directions. Their sides form nearly parallel lines. The distances between structures are not arbitrary. They reflect spatial relationships that appear measured. One of the more frequently discussed observations concerns the slight diagonal offset of the three main pyramids. Some have suggested symbolic alignments with stars in Orion's belt. This idea, popularised in alternative literature, remains controversial within academic circles. While the pyramid's arrangement bears a superficial resemblance to the three-star pattern, statistical analyses question the precision of the match. Regardless of astronomical interpretations, the terrestrial layout itself demonstrates systematic planning. Large areas of bedrock were quarried to create space for temples and courtyards. Blocks removed from the plateau were repurposed into construction material. This dual function, quarry and building site, reflects efficient resource use. The plateau also contains mastaba tombs belonging to officials and nobles. These smaller rectangular structures cluster around the main pyramids. Their placement follows grid-like arrangements in some areas, suggesting that burial plots were assigned within a structured plan. Engineering a landscape requires foresight. The builders needed to account for slope, drainage, and foundation stability. The plateau's limestone varies in hardness and stratification. Some layers are more resistant, others crumble more easily. Selecting stable zones for heavy monuments would have required geological awareness, even if not formalised in modern terms. Evidence of levelling trenches around the Great Pyramid indicates that water may have been used to establish horizontal reference lines. Channels cut into bedrock could have been filled with water to identify high and low points. By shaving down elevated sections, builders achieved a relatively even base across hundreds of metres. Such large-scale levelling transforms a natural landscape into a constructed platform. The pyramids do not merely decorate the plateau, they reshape it. The alignment of internal pyramid passages also ties into the broader orientation. The descending passage of the Great Pyramid points toward a region of the northern sky that once contained circumpolar stars. This alignment would have required careful angular measurement relative to the horizon. Transferring such measurements from observation point to construction site involves systematic surveying. Across the plateau, quarries reveal extraction marks consistent with organised stone removal. Blocks were cut from bedrock using trenches, leaving rectangular impressions. The extracted blocks were then transported short distances to nearby construction zones. The entire site functioned as an integrated system of quarrying, shaping and assembly. It is tempting to imagine each pyramid built independently, but archaeological evidence suggests overlap in workforce and logistics. Worker villages discovered near Giza indicate centralised coordination. Rations, housing and medical care were provided. This was not random labour. It was state-managed infrastructure. The causeways linking pyramids to valley temples were not decorative additions. They served functional roles in transporting materials and facilitating ceremonial processions. Their straightness and consistent width indicate pre-planned routes. When standing on the plateau at sunset, one can see how the pyramids align visually with the horizon. Their silhouettes interact with the sky in predictable ways. Whether these visual alignments were part of the initial design or a byproduct of practical orientation is uncertain, but the cumulative effect reinforces coherence. Modern urban planners often design spaces with sightlines and axial relationships. The Giza Plateau displays similar characteristics, though on a monumental scale. The plateau's layout also interacts with the Nile's historical position. During the Old Kingdom, the Nile's floodplain extended closer to the site. Valley temples connected via waterways allowed stone to be transported by boat. Positioning monuments relative to navigable channels required geographic planning. Over time, the Nile shifted. The plateau's relationship to the river changed. Yet the original placement reflects an understanding of landscape dynamics at the time of construction. Geophysical surveys have identified subsurface anomalies, suggesting additional structures buried beneath sand. Whether these represent storage areas, unfinished projects, or later additions remains under investigation. The plateau may still conceal aspects of its original layout. What emerges from this broader view is the sense that the Giza Plateau was engineered as a unified complex rather than assembled incrementally without coordination. The pyramids, temples, quarries, causeways, and tombs form a network tied together by alignment, resource flow, and geometry. This does not require lost high technology. It requires organisation, surveying skill, and an architectural vision extending beyond individual monuments. The perception of mystery often arises when large achievements are viewed through modern assumptions about ancient simplicity. Yet the archaeological record demonstrates that Egyptian administrators were capable of coordinating vast projects. Written records from other periods detail workforce management and supply chains. The Giza Plateau exemplifies this administrative capability in stone. Still, the scale and coherence of the layout continue to invite admiration. Aligning massive structures to cardinal points, levelling hundreds of metres of bedrock, integrating quarrying into construction, and maintaining consistent orientation across multiple monuments represent cumulative precision. It is not that the plateau behaves in ways that defy explanation. It behaves in ways that demand respect for planning and execution. As attention shifts once more from landscape scale back towards specific technical phenomena, another dimension of the discussion emerges. Within the chambers of the Great Pyramid, certain acoustic properties have been measured. Sound behaves differently inside enclosed granite rooms. Vibrations resonate. Frequencies linger. The question then becomes not only how stone was cut and placed, but how space within stone interacts with physical forces such as sound. And whether any of these interactions were intentional or incidental remains part of the ongoing exploration of ancient Egyptian technology and its enduring complexity. Inside the Great Pyramid, away from the bright glare of the plateau and the shifting desert wind, the air changes. Sound changes with it. Footsteps echo differently. Voices linger a fraction longer than expected. In narrow passages, a cough travels ahead and behind at once. In larger chambers, tones gather and return in softened waves. The internal spaces of the Great Pyramid were not carved for decoration. They were shaped from stone and then enclosed by stone. Granite beams weighing tens of tons form ceilings. Limestone blocks create walls and corridors that narrow and rise. The structure compresses space in some areas and opens it in others. When sound enters these chambers, it interacts with geometry. Modern researchers equipped with microphones and frequency analyzers have measured acoustic properties inside the so-called King's Chamber. This chamber, constructed from massive granite blocks, has a rectangular shape with flat surfaces and sharp corners. Its proportions create standing waves at specific frequencies. When certain tones are produced, resonance builds, reinforcing those frequencies within the room. This is not unusual in enclosed spaces. Every room has resonant frequencies determined by its dimensions and the materials of its surfaces. In modern architecture, concert halls are designed to manage resonance deliberately. The question at Giza is not whether resonance exists, but whether the chambers were designed with acoustic properties in mind. Some experiments have demonstrated that the King's Chamber resonates strongly around particular low frequencies. When a tone matching one of these frequencies is generated, the sound seems to intensify and sustain longer than others. The granite surfaces reflect sound efficiently due to their density and hardness. Granite is not an absorbent material. It does not dampen sound significantly. Instead, it reflects acoustic energy, allowing waves to bounce between parallel surfaces. In a rectangular room, These reflections can create patterns of reinforcement and cancellation. The presence of resonance alone does not prove intentional acoustic engineering. Rectangular rooms of certain proportions will naturally exhibit resonant behaviour. However, the specific dimensions of the chamber have led some to question whether the acoustic effects were incidental or purposeful. It is important to approach such claims carefully. There is no inscription within the pyramid stating that the chamber was designed as a resonant device. There are no surviving records describing acoustic rituals performed within its walls. Still, ancient Egyptians were not unfamiliar with sound as a ritual element. Temples featured chanting, music, and ceremonial recitations. Enclosed stone spaces would amplify and shape such sounds. Some researchers have proposed that resonance in the king's chamber may have had symbolic or experiential significance. A low sustained tone in a granite chamber produces a vibration that can be felt as much as heard. The physical sensation of sound could have enhanced ritual experiences. Experiments conducted by acoustic engineers have shown that even modest vocal tones can excite certain frequencies within the chamber. However, sustaining strong resonance typically requires specific pitch alignment and sufficient amplitude. There have also been claims that the entire pyramid structure behaves as a resonant cavity at certain frequencies. Computational models have been developed to simulate how electromagnetic or acoustic waves interact with the pyramid shape. Some studies suggest that under specific conditions, energy concentration might occur in particular areas. Such simulations often rely on idealized models. The real pyramid, with its internal voids, varying material densities and structural irregularities, complicates straightforward resonance predictions. It is also worth noting that the pyramid is not hollow. Its mass is predominantly solid limestone. The internal chambers occupy a small fraction of its volume. Any large-scale resonance would be heavily dampened by the surrounding stone. Beyond the king's chamber, the Grand Gallery presents a different acoustic profile. Its tall, corbelled ceiling and sloping floor create a long, narrow volume. Sounds produced within the gallery reflect and travel differently than in rectangular rooms. Echoes may overlap, creating layered auditory effects. Visitors who hum softly in these spaces often notice unusual reverberation, yet perception can be influenced by expectation. Knowing that one stands within an ancient monument predisposes the mind to interpret sensory experiences as significant. The role of sound in ancient Egyptian architecture remains speculative. Unlike Greek theatres, which were clearly designed for acoustic performance, Egyptian pyramids lack explicit evidence of sonic function. However, the Egyptians were attentive to orientation, geometry, and proportion. It is not unreasonable to consider that interior space might have been shaped with multiple factors in mind. There is also the matter of the granite coffer within the king's chamber. When struck gently, granite can produce a clear tone. Some have experimented by tapping the coffer and listening to its resonance. The resulting sound is brief and subdued, consistent with the properties of dense stone. Claims that the coffer functioned as an advanced resonator or energy device lack credible evidence. The coffer appears to have served as a sarcophagus, consistent with burial practices of the era. Still, the combination of heavy granite construction and enclosed geometry naturally produces acoustic effects that modern visitors find intriguing. Acoustic measurement equipment placed inside the pyramid has recorded reverberation times and frequency responses. These measurements confirm that the chambers reflect sound efficiently. They do not confirm an advanced technological purpose. It is also important to consider structural necessity. Granite was used in the king's chamber not for acoustic reasons but for strength. The chamber lies beneath millions of tons of stone. Granite beams distribute weight and prevent collapse. The use of granite likely reflects structural considerations rather than acoustic design. Resonance, then, may be a byproduct of material choice and geometry rather than a primary objective. However, ancient cultures often blended structural, symbolic, and experiential elements. A chamber that supports weight effectively and produces a distinct acoustic atmosphere would not have been dismissed as irrelevant. There have also been explorations into whether vibrations could have been used during construction. Some speculative theories propose that sound or resonance assisted in stone shaping or movement. These ideas remain unsupported by archaeological evidence. Granite does not respond significantly to low-amplitude acoustic vibrations in a way that would ease cutting or transport. The energy required to meaningfully alter granite's structure far exceeds what human vocalization or simple instruments could produce. The pyramid's acoustic properties are therefore best understood as an interesting secondary characteristic of its architecture. Even so, standing inside a granite chamber where sound lingers differently than in everyday spaces creates a distinct sensory experience. Ancient builders may have been aware of this effect, even if not in quantitative terms. The broader theme continues: precision in stone cutting, symmetry in layout, and resonance in enclosed spaces all arise from the same material choices and geometric planning. As the investigation moves outward again, from interior chambers back to the question of moving enormous blocks of stone into position, the focus returns to physical logistics. Granite beams in the king's chamber weigh tens of tons. Blocks forming the pyramid's core and casing required transport across both river and desert. How such masses were moved and positioned with sufficient accuracy to maintain alignment remains another component of the larger inquiry. Sound may echo within granite walls, but those walls first had to be quarried, transported, lifted, and set in place. And it is in the mechanics of that movement, sledges, ramps, leverage, and coordination, that the next layer of examination unfolds, shifting from vibration within stone to the challenge of persuading stone itself to move across sand and into the sky. Granite does not float on sand. It does not roll easily across uneven ground. It does not forgive imbalance. And yet, across the Giza Plateau and beyond, blocks weighing tens of tons were not only moved but placed with deliberate precision. The question of cutting and shaping stone leads naturally to another equally practical challenge. How did ancient Egyptians move masses that modern construction companies would approach with cranes and heavy machinery? The stones used in the Great Pyramid vary in size. Many core blocks weigh between 2 and 3 tons. That is heavy but manageable with coordinated labour and simple mechanical aids. The granite beams above the king's chamber, however, weigh far more, some exceeding 40 or 50 tons. The granite used in the pyramid complex originated in Aswan, nearly 800 kilometres to the south. Transporting such material from quarry to construction site required multiple stages: extraction, movement to the Nile, river transport, unloading, overland hauling, and final placement. The extraction stage is visible at Aswan, where unfinished obelisks and quarry marks remain. Workers cut trenches into the granite bedrock, isolating blocks from the surrounding stone. Dolerite pounding stones were used to fracture and shape rough outlines. Once separated, blocks needed to be shifted from quarry floor to riverbank. The Nile served as Egypt's primary transportation artery. During the annual inundation, water levels rose, bringing navigable channels closer to quarry sites and construction zones. Relief carvings depict large statues transported on barges, secured and accompanied by workers managing ropes and rudders. Granite blocks could be loaded onto barges using ramps and coordinated manpower. The buoyancy of water reduces effective weight, making river transport efficient relative to overland hauling. Once at Giza, however, the blocks needed to be unloaded and moved uphill to the plateau. This stage remains one of the most discussed aspects of pyramid construction. Wall reliefs from the tomb of Jehuti-Hotep show a colossal statue being transported on a wooden sledge, pulled by hundreds of workers. A figure at the front pours water onto the sand before the sledge. This detail has gained attention because wet sand reduces friction. Modern experiments have confirmed that dampening sand increases its load-bearing capacity and reduces resistance to sliding. By controlling moisture levels, workers can halve the force required to pull heavy loads across sand. The sledge system is simple, yet effective. A flat wooden platform supports the stone. Ropes attached to the front allow teams to pull in unison. Rollers are not ideal on soft sand as they sink. Sliding over prepared tracks is more practical. Archaeological evidence suggests that prepared pathways may have existed. Remnants of possible ramps and compacted surfaces have been identified near pyramid sites. The exact configuration of ramps remains debated. Straight ramps, zigzag ramps, internal ramps, and circular ramps have all been proposed. A straight ramp rising from ground level to the pyramid's top would require enormous material, potentially rivaling the pyramid itself in volume. This has led some researchers to favour more compact ramp designs that spiral around the structure or use internal passages. Regardless of ramp configuration, moving multi-ton blocks upward requires incremental lifting and stable footing. Leverage tools such as wooden levers could have been used to raise stones in small steps, placing packing material beneath them to gain height gradually. The lifting of granite beams into the king's chamber remains particularly intriguing. These beams sit tens of metres above ground level. Positioning 40-ton blocks at that height without modern cranes required coordinated engineering. Some propose that the beams were raised along ramps extending to the chamber level before upper courses were completed. Others suggest step-by-step levering combined with scaffolding. The absence of preserved ramps complicates definitive conclusions. Mud brick ramps would have eroded. Stone ramps may have been dismantled and reused. What remains is indirect evidence: tool marks, quarry sites, and the finished structure. Critics of conventional explanations sometimes argue that moving such heavy stones is beyond human capability without advanced technology. This underestimates coordinated labour. Modern demonstrations have shown that teams of workers using ropes and sledges can move stones weighing dozens of tons over prepared surfaces. The challenge is not impossibility, but scale and organisation. Coordinating hundreds of workers to pull in rhythm requires leadership, communication, and discipline. Ancient Egypt possessed hierarchical administration capable of mobilising labour forces seasonally, particularly during Nile floods when agricultural work paused. Worker villages discovered near Giza provide insight into daily life. Housing remains, bakeries and medical facilities indicate that labourers were provisioned systematically. This was not chaotic improvisation. It was managed infrastructure. There is also evidence of sled tracks preserved in desert areas near other ancient sites. These tracks support the idea that sliding heavy loads was standard practice. The question then shifts from feasibility to efficiency. How long would it take to move thousands of blocks into position? Estimates vary depending on assumed workforce size and daily output. Some calculations suggest that with thousands of workers, placing a block every few minutes would suffice to complete a pyramid within decades. Such rates are ambitious but not absurd in the context of organised labour over long periods. Granite beams from Aswan would have required special handling due to their weight and brittleness. Cracks during transport would waste immense effort. Careful packaging, perhaps using cushioning materials or controlled lowering systems, would have been necessary. There is also the matter of final placement precision. Aligning heavy blocks with minimal gaps requires incremental adjustments. Workers likely use levers to nudge stones into position once near their final location. Small shifts under heavy load demand patience. Some researchers have speculated about the use of counterweight systems within the pyramid to lift blocks internally. A vertical shaft with descending counterweights could assist in raising stones. Such systems would require careful design and coordination. To date, no direct evidence confirms the use of counterweight elevators in the Great Pyramid. The idea remains speculative but mechanically plausible. What is certain is that ancient Egyptians were adept at manipulating stone at scale. The transportation of obelisks weighing hundreds of tons in later periods demonstrates continuity in heavy stone movement. The notion that stones shouldn't move reflects modern perception rather than physical law. Stone obeys gravity and friction. With sufficient force applied strategically, it moves. Yet acknowledging capability does not eliminate the sense of accomplishment. Moving and placing millions of blocks with consistent alignment across a massive structure remains a feat of coordination unmatched in many subsequent periods. The logistics of quarrying, transporting, shaping, and placing granite beams inside the pyramid connect directly to earlier discussions of cutting precision. A block shaped with care at Aswan must be delivered intact to Giza. A lid carved to fit a box at Saqqara must be lowered without fracture. Transportation and shaping are not separate puzzles. They are phases of a continuous process. As the investigation progresses, attention turns from movement itself to a deeper question. Were the methods employed purely incremental refinements of simple tools, or did specialized machines, constructed primarily of wood and rope, play a larger role than often depicted? The distinction matters not because it implies advanced lost civilizations, but because it shapes our understanding of ancient engineering sophistication. If wooden frames, weighted feeds, and guided sled systems were common, then ancient Egyptian technology may have been more mechanically organized than simplified illustrations suggest. And as the exploration continues, the focus will move from the visible evidence of stone movement to the subtler question of whether entire technological systems once existed that left little trace beyond the stone they shaped and the monuments they assembled. When people hear the phrase lost technology, the imagination often runs ahead of the evidence. Images of hidden engines, vanished power sources, or forgotten civilizations tend to surface quickly. But there is a quieter and far more grounded possibility that deserves attention. What if nothing supernatural was ever involved? What if what has been lost is not advanced machinery in the modern sense, but refined methods, specialized workshop systems, and mechanical techniques built mostly from materials that do not survive thousands of years? Stone remains. Wood does not. Rope decays. Leather rots. Metal is melted and reused. A civilization can leave behind millions of tons of limestone and granite, while leaving almost no trace of the wooden frames, measuring tools, sledges, clamps, scaffolds, and rigs that made their manipulation possible. This distinction matters. When modern textbooks depict pyramid construction, the illustrations are often simplified. A few workers with ropes, a ramp, a sledge. It conveys the basic idea without implying complexity. But simplicity in illustration does not necessarily reflect simplicity in practice. Consider how modern construction works even without electricity. Remove cranes and diesel engines, and what remains? Levers, pulleys, counterweights, screw jacks, frames that distribute force, systems that multiply mechanical advantage. None of these devices require steel in the modern industrial sense. Many can be built from hardwood and rope. There is no reason in principle that ancient Egyptians could not have developed sophisticated mechanical aids, constructed primarily of organic materials. Such devices would leave minimal archaeological trace. The phrase lost machines does not need to imply advanced industrial equipment. It could simply refer to specialized rigs, drill frames with weighted feeds, guided saw frames with tensioning systems, sled platforms engineered for stability, lifting systems that employed compound leverage. If a wooden drill press-like frame existed, it would likely not survive 4,500 years in the Egyptian climate unless preserved under extraordinary conditions. Even then, metal fittings would likely have been removed and recycled. Archaeology is shaped by preservation bias. Stone and ceramics dominate the record because they endure. Organic materials are underrepresented. In the case of granite drill cores with spiral grooves, one explanation is not that ancient Egyptians possessed electric drills, but that they may have built stable, vertical frames to control feed rate and alignment. A weighted stone or sandbag could provide constant downward pressure. A flywheel effect could smooth rotational motion. Such a system would dramatically increase consistency, compared to handheld bow drilling alone. Similarly, when carving thin-walled stone vases, a simple horizontal spindle supported by wooden stands could allow the stone blank to rotate, while abrasives shaped its surface. The artisan would not need to hold the piece freehand. Stability increases precision. These are not extraordinary machines. They are practical mechanical aids. The absence of preserved examples leaves room for debate. Yet absence is not evidence of non-existence. It simply limits certainty. There is also the question of specialization. Large-scale construction projects likely involved workshops dedicated to specific tasks. Quarrying teams, transport crews, shaping artisans, finishing specialists, surveyors. Each group could have refined its own tool systems. Knowledge transmission in ancient Egypt was likely apprentice-based. Methods may have been passed orally and through demonstration rather than written manuals. If a workshop tradition declined or shifted focus, its methods could fade without leaving textual record. Historical examples from other cultures demonstrate that technological techniques can be lost. Roman concrete, once widely used, was not replicated with the same durability for centuries after the fall of the Roman Empire. Damascus steel, famous for its patterned blades, became difficult to reproduce after certain production chains were disrupted. These examples show that technology does not always progress linearly. It can plateau, fragment, and disappear depending on social and economic factors. In Egypt's case, the Old Kingdom produced monumental stone architecture on a scale not matched in later periods. Later dynasties built impressive temples and statues, but pyramid construction declined in size and precision. Whether this reflects economic changes, political shifts, or technological evolution remains debated. The idea of lost methods fits within known historical patterns. Techniques optimized for specific state-sponsored mega-projects may not persist when those projects cease. Another possibility is that ancient Egyptian engineering was never mysterious, but simply underestimated. Modern observers accustomed to powered machinery may find it difficult to internalize how effective coordinated labor and mechanical advantage can be. A lever multiplies force. A pulley changes direction and distributes load. A compound pulley system dramatically reduces required effort. None of these require advanced metallurgy. Rope and hardwood suffice. Even a simple A-frame lifting device combined with counterweights could allow vertical positioning of heavy stones with surprising efficiency. What we call machines today often consist of assemblies of simple components. If those components are made from perishable materials, their disappearance is unsurprising. Still, one must avoid drifting too far into speculation. Proposing wooden drill presses or stone lathes requires evidence beyond plausibility. So far, direct archaeological confirmation remains limited. Some artifacts show wear patterns consistent with repeated tool use. Copper tools recovered from sites display signs of abrasion. Dolerite pounders show impact wear. These physical traces confirm stoneworking but do not fully reveal the mechanical setups employed. There is also the possibility that ancient Egyptians exploited methods we have not fully reconstructed, because modern experiments often operate under limited time and funding constraints. A technique that requires months of refinement to optimize may be dismissed prematurely in short-term studies. Ancient craftsmen, by contrast, could invest years perfecting methods. Their economic framework differed. Labour was abundant during flood seasons. Monumental construction served political and religious purposes beyond immediate utility. In such a context, efficiency did not necessarily mean speed. It meant reliability and repeatability. The question then becomes one of mindset. Do we assume that because certain mechanical devices have not been found, they did not exist? Or do we accept that much of ancient technology was built from materials unlikely to survive? The distinction between lost machines and lost methods may ultimately be semantic. A method implemented through a mechanical system is in effect a machine. The key difference lies in scale and implication. There is no credible evidence that ancient Egyptians possessed industrial-grade metalworking capable of producing hardened steel drills. There is no reliable proof of electricity, combustion engines, or advanced metallurgy in Old Kingdom contexts, but there is strong evidence of organisational capacity, geometric understanding, and material mastery. Between primitive hand tools and modern industrial machinery lies a broad spectrum of mechanical ingenuity. Ancient Egypt almost certainly occupied a space somewhere within that spectrum more complex than the simplest illustrations suggest. As this exploration continues, the focus will return to the textual record. Ancient Egyptian inscriptions are abundant in certain categories: religious texts, administrative accounts, royal achievements, but they are curiously sparse when it comes to detailed descriptions of engineering processes. The next step is to examine what the oldest texts actually say about construction and craftsmanship, and perhaps more importantly what they do not say, because silence in the record can be as revealing as explicit description, especially when stone stands in quiet contrast to words that never mention the techniques that shaped it. Ancient Egypt left behind a great many words. Temple walls are covered in hieroglyphs. Tombs preserve prayers, offerings, and invocations to gods. Administrative papyri record deliveries of grain, livestock counts, and worker assignments. Royal inscriptions celebrate victories and building projects. The civilization was not silent, and yet when it comes to the precise technical details of how massive granite blocks were cut, how drill rigs were constructed, or how thin-walled stone vases were shaped from diorite, the record grows noticeably quiet. The oldest extensive religious texts, known as the Pyramid texts, appear inside the pyramids of the 5th and 6th dynasties, later than the Great Pyramid itself. These inscriptions focus on the king's journey to the afterlife, his transformation into a star, and his union with divine forces. They speak in symbolic language. They do not describe quarrying methods or tool designs. Administrative records from later periods mention deliveries of stone and workforce organisation. Papyrus fragments document shipments of limestone, labour rotations, and food rations for workers. They confirm that large-scale construction was state-managed. They demonstrate logistical sophistication. What they do not provide is a manual. There is no surviving Egyptian equivalent of a technical handbook explaining how to drill granite efficiently or how to level a 230-metre square to within centimetres. This absence has fueled speculation. Some argue that such knowledge was secret, restricted to elite priest engineers. Others suggest that practical knowledge was considered too commonplace to record formally. It is worth remembering that most ancient societies did not document everyday technical processes in detail. Crafts were transmitted through apprenticeship. A master showed an apprentice how to hold a tool, how to feel resistance in stone, how to judge flatness by sight and touch. The knowledge lived in hands rather than texts. When Egyptian inscriptions mention building projects, they often emphasize scale and devotion rather than method. Pharaohs proclaim that they raised monuments of eternal stone, or built temples of millions of years. The rhetoric celebrates permanence and divine favour, not engineering diagrams. There are reliefs depicting stone transport. Scenes show workers pulling statues on sledges. Supervisors stand nearby. Water is poured onto sand. These images provide valuable clues. They confirm that sledges and coordinated labour were used. They do not reveal precise calculations of friction or ramp gradients. There are also depictions of stoneworkers shaping blocks with chisels and pounders. Such scenes illustrate stages of labour, but remain schematic. They are not instructional blueprints. The absence of detailed technical documentation does not imply that techniques were primitive. It reflects cultural priorities. Egyptian writing served religious, political, and administrative functions. Technical manuals may have existed on perishable materials and not survived, or they may never have been formalised in writing. Some scholars suggest that high-level architectural knowledge may have been restricted within specific temple or royal circles. Master builders, sometimes referred to in inscriptions as overseers of works, likely possessed practical expertise. Their titles indicate authority, not necessarily textual legacy. The story of Imhotep, often associated with the step pyramid of Djoser, illustrates this pattern. Imhotep is remembered as a polymath, architect, physician, advisor. Later traditions elevated him to semi-divine status. Yet no technical treatise authored by him survives. What the texts do reveal is a culture deeply concerned with order, proportion, and alignment. The concept of Ma'at, cosmic balance and harmony, permeates religious and royal language. Maintaining order in architecture would align with maintaining order in society. Mathematical papyri from later periods, such as the Rind mathematical papyrus, demonstrate that Egyptian scribes understood geometry and arithmetic. They calculated areas, volumes, and slopes. These documents, though centuries later than the Great Pyramid, show that practical mathematics was part of the intellectual landscape. The Rind papyrus includes problems involving the seked, a measure related to pyramid slope. This indicates that Egyptian builders had a systematic way to define and replicate specific angles. It supports the idea that pyramid geometry was deliberate rather than accidental. Still, the papyri do not describe granite drill feed rates or lathe designs. They focus on calculations, not tool mechanics. There is also the matter of what might be considered obvious knowledge at the time. Techniques that are second nature to craftsmen are rarely written down unless there is a need to standardise or teach at scale beyond apprenticeship. If stoneworkers operated within tightly knit communities, their methods could persist orally for generations without ever being inscribed in hieroglyphs. The archaeological record is shaped by what people chose to record and what survived. Papyrus decays in humid conditions. Only in exceptionally dry environments do fragments endure. Even then, survival is partial. What remains from Old Kingdom Egypt is a fraction of what once existed. To conclude that absence of technical manuals means absence of sophisticated methods would be premature. At the same time, the lack of explicit documentation means that modern reconstructions rely heavily on physical evidence and experimental archaeology. Stone becomes the primary text. Tool marks are read like sentences. Groove patterns become clues. The tension between written silence and material precision fuels much of the discussion surrounding ancient Egyptian technology. Some alternative interpretations claim that the silence is deliberate, that knowledge was intentionally concealed or later suppressed. Such claims lack direct evidence. Cultural secrecy cannot be assumed without supporting documentation. A more restrained interpretation recognizes that ancient record-keeping did not prioritize mechanical exposition. Religious legitimacy and royal propaganda took precedence. There are occasional references to specialized craftsmen and workshops. Inscriptions mention chiefs of artisans and overseers of sculptors. These titles confirm structured labor hierarchies. They do not detail the tools in their hands. The broader lesson is that technology can exist without textual description. Many pre-industrial societies developed sophisticated methods without leaving behind formal engineering treatises. The absence of explicit technical accounts in Old Kingdom texts neither proves nor disproves advanced mechanical aids. It simply narrows the evidentiary base to archaeology and experiment. As the inquiry continues, attention shifts from silence in texts to the possibility that some techniques were inherited rather than invented during the Old Kingdom. If certain methods appear suddenly refined in early periods, perhaps they were the culmination of earlier experimentation. The next layer of exploration considers whether Egyptian stoneworking expertise was built gradually over centuries, or whether it reflects a transfer of knowledge from a prior, less documented phase of development that shaped what later became monumental tradition. When a technology appears fully formed in the archaeological record, the instinct is often to ask when it was invented. But sometimes the better question is whether what we are seeing represents invention at all, or inheritance. Skills rarely emerge in isolation, they accumulate. They are refined, passed along, and adjusted quietly across generations long before they are expressed in monumental form. In Egypt, some of the most technically refined stone artifacts predate the Grand Pyramids. Pre-dynastic stone vases carved from diorite and granite show high levels of symmetry and control. By the time the Old Kingdom begins erecting pyramids on the Giza Plateau, stoneworking is not an experimental craft, it is established. This chronological sequence suggests continuity rather than sudden innovation. The earliest monumental stone architecture in Egypt is the step pyramid of Djoser at Saqqara, constructed during the Third Dynasty. Its architect, Imhotep, transitioned from traditional mud brick construction to large-scale stone building. The step pyramid complex includes extensive stone walls carved to resemble earlier wooden and reed structures. The builders were not inventing stonework from nothing. They were adapting existing architectural language into more durable material. That adaptation required prior experience with stone. Quarries at sites such as Aswan and Tura reveal extraction techniques that must have evolved over time. Workers learned how to identify natural fracture lines, how to isolate blocks efficiently, how to transport them without catastrophic cracking. These skills imply experimentation long before they were scaled to pyramid size. The refinement visible in early dynastic stone vessels further reinforces the idea of gradual mastery. Some of these vases date to a period before centralized pyramid construction. Their precision implies workshops already comfortable manipulating hard stone. If Old Kingdom builders achieved impressive granite shaping, it may not reflect a technological leap within a single generation. It may represent the maturation of a tradition centuries in development. Inheritance does not require a lost civilization. It requires time. Knowledge transmitted through apprenticeship leaves no sudden marker in the record. Each generation improves slightly upon the last. Techniques that appear advanced when viewed in isolation may be the endpoint of incremental refinements that left few dramatic traces. This perspective also reframes the so-called precision problem. Instead of asking how ancient Egyptians suddenly achieved millimetre-level tolerances with copper tools, one might consider how long they had been perfecting abrasive methods before those tolerances became visible in monumental contexts. The Nile Valley supported settled communities for millennia before pyramid construction. Craft specialization likely deepened as social complexity increased. The emergence of centralized authority during the early dynastic period would have consolidated skilled labor under state supervision. Under such conditions, workshops could standardize methods, refine measurement systems, and experiment with mechanical aids without the pressure of short-term efficiency. There is also archaeological evidence of continuity in quarrying methods across centuries. Dolerite pounding stones appear in multiple contexts. Copper tools are found in varying forms. Tool marks evolve subtly, but do not indicate abrupt technological discontinuity. The idea of inheritance also applies to geometry. The precise alignment of the Great Pyramid did not require spontaneous mathematical genius. It required accumulated astronomical observation. Generations of skywatching priests could refine cardinal direction measurement gradually. By the Fourth Dynasty, such knowledge may have been robust enough to support ambitious alignment projects. It is worth noting that technological peaks are often tied to political stability and resource concentration. The Old Kingdom enjoyed centralized power capable of mobilizing labor and materials on unprecedented scales. When later periods experienced fragmentation, monumental stone construction declined. This pattern does not necessarily imply technological loss. It may reflect shifting priorities and resource allocation. Still, there are cases where specific crafts appear to diminish in refinement over time. Some later Egyptian stonework lacks the crispness of earlier examples. Whether this reflects declining skill, economic constraint, or stylistic change remains debated. If certain workshop traditions were tightly linked to royal patronage, their decline could result in gradual loss of specialized techniques. Inheritance works both ways. Knowledge can be passed down, but it can also fade if not sustained. The absence of detailed technical texts complicates tracing this lineage precisely. Archaeologists rely on stylistic and material analysis to infer continuity. Toolmark patterns, quarry locations, and artifact distribution offer indirect evidence. Some researchers propose that earlier phases of Egyptian civilization may have included experimental approaches now lost or absorbed into later practices. For example, early dynastic stone vessels sometimes display a level of intricacy that seems disproportionate to their historical context. Yet caution is essential. Human ingenuity often appears surprising when viewed through modern assumptions about linear progress. The fact that early artisans achieved impressive results does not require hidden predecessors beyond the known archaeological record. Inheritance can operate within documented history. Consider the possibility that the stoneworking expertise evident in the Serapeum boxes and granite beams reflects centuries of refinement beginning with small-scale artifacts. Techniques perfected on handheld objects may have scaled upward gradually. The transition from carving a thin-walled vase to shaping a flat granite surface inside a massive box is not a leap into the unknown. It is an expansion of the same abrasive principles applied at different scales. The cumulative effect of incremental innovation can appear dramatic when examined retrospectively. There is also the psychological dimension. Modern observers often equate technological sophistication with advanced metallurgy or mechanization. But ancient technological sophistication may have centered on process control, measurement discipline, and labor organization. A culture deeply invested in ritual permanence may channel extraordinary effort into mastering stone. That mastery, passed from artisan to artisan, becomes tradition rather than novelty. Inheritance also implies resilience. Even if specific tools evolved, the underlying knowledge of material behavior persisted. Craftsmen knew how granite responded to impact, how sand behaved under pressure, how to test flatness by feel. Such tacit knowledge rarely appears in inscriptions, it lives in practice. The broader narrative then shifts from mystery toward continuity. Rather than asking whether ancient Egyptians possessed lost high technology, one might ask how far back their stoneworking tradition extends, and how its refinement accumulated quietly. This perspective does not eliminate all open questions. It reframes them. If techniques were inherited and refined over centuries, it raises another question. Could some knowledge have been gradually forgotten as political structures changed? When state-sponsored mega-projects ceased, did specialized workshops dissolve, taking with them nuanced methods that were never written down? This possibility introduces the next layer of inquiry. Technological decline need not involve catastrophe. It can result from gradual shifts in patronage, resource allocation, and social organization. And as the exploration continues, attention turns to the possibility that some methods, once common within tightly controlled workshops, may have faded not through dramatic collapse, but through quiet attrition, leaving behind stone artifacts that seem more precise than later imitations. Technological knowledge does not always disappear in a single dramatic moment. It does not always vanish with conquest or collapse. More often, it fades gradually, one workshop at a time, one generation at a time, when the conditions that sustained it change. Ancient Egypt did not remain politically or economically static. The Old Kingdom, which saw the construction of the largest pyramids, eventually gave way to periods of decentralization and regional power struggles. Royal authority weakened, resources shifted, monumental stone projects declined in scale. When centralized power fragments, specialized industries tied closely to state sponsorship can suffer. Large-scale quarrying operations require coordination, funding, and logistical support. If that support diminishes, the workshops responsible for refined granite shaping may disperse. This does not imply a catastrophic loss of all stoneworking ability. It suggests selective decline. Crafts that depend on consistent high-level patronage are vulnerable when patronage changes. In the Old Kingdom, massive pyramids and granite chambers served ideological and political purposes. They embodied permanence and divine authority. When later dynasties chose different expressions of power, rock-cut tombs, temples built from smaller blocks, or mud brick structures, the demand for extreme granite precision may have lessened. As demand shifts, so does specialization. If a particular method for drilling granite efficiently required a team trained in its operation, and if that team was no longer needed at scale, the technique might persist only in limited contexts. Over time, without continuous application, refinement could erode. History provides parallels. The production of Roman concrete with specific volcanic ash created structures that endured millennia. After the Western Roman Empire's decline, the exact composition and widespread use of that formula diminished. The knowledge did not vanish instantly. It faded as trade networks and administrative structures changed. Similarly, Damascus steel, known for its distinctive patterns and strength, became difficult to reproduce when specific ore sources and production chains were disrupted. The technique was not mystical. It was embedded within economic systems. In Egypt, the end of pyramid building on a grand scale coincided with changes in burial practices. Kings of the New Kingdom were buried in rock-cut tombs in the Valley of the Kings, rather than beneath massive pyramids. Temple construction flourished, but architectural emphasis shifted. Granite continued to be used, but perhaps not with the same frequency or precision in certain applications. Workshops may have adapted to new requirements. Gradual forgetting does not require cultural amnesia. It can occur when specific constraints disappear. If a technique is optimized for shaping 50-ton granite beams for internal pyramid chambers, and such chambers are no longer built, the incentive to maintain that optimization diminishes. Over generations, skills narrow. Apprentices learn what is necessary for current demand. Subtle refinements may be omitted if they no longer provide advantage. The archaeological record reflects change. Later Egyptian monuments often display high craftsmanship, but the style and techniques evolve. The immense scale of 4th Dynasty pyramids was never repeated in quite the same way. This raises a measured question. Were certain Old Kingdom techniques so closely tied to the ideological moment of pyramid construction that they faded once that moment passed? It is also possible that knowledge was compartmentalized. Certain techniques may have been guarded within specific guilds or priestly circles. If political upheaval disrupted those groups, continuity would weaken. However, caution is necessary. There is no direct evidence of secret knowledge being intentionally suppressed or lost. The decline of large pyramids can be explained by economic and political factors without invoking technological disappearance. Stoneworking did not cease after the Old Kingdom. Temples such as Karnak and Luxor display impressive stone construction. Obelisks weighing hundreds of tons were erected during later periods. This indicates continued capability in quarrying and transport. Yet the specific combination of scale, precision, and internal granite chamber construction seen at Giza remains distinctive. It is possible that Old Kingdom builders invested extraordinary resources into a limited time frame. When later dynasties chose different architectural priorities, the focus shifted accordingly. The question of gradual forgetting intersects with the earlier idea of inheritance. Knowledge accumulates over time, but it can also dissipate if not actively maintained. Craft traditions thrive under stable patronage. They wither under neglect. The absence of detailed technical texts exacerbates the issue. If methods were transmitted orally, their survival depended on uninterrupted apprenticeship chains. Political fragmentation could disrupt these chains. Environmental factors also play a role. Quarry sites can be abandoned. Toolmaking workshops can be repurposed. Without sustained use, infrastructure decays. It is important not to romanticize the idea of lost knowledge. There is no compelling evidence that Egyptians possessed dramatically more advanced metal tools in the Old Kingdom than later periods. Copper remained dominant until iron became more widespread in subsequent centuries. The gradual forgetting hypothesis does not require lost advanced metallurgy. It concerns procedural refinement. Consider the stone vases again. The highest precision examples cluster in early periods. Later stone vessels often display simpler forms. Whether this reflects declining skill or changing aesthetic preference remains uncertain. In some cases, later artisans may have found that simpler techniques were sufficient for contemporary needs. Complexity beyond necessity tends to be abandoned in practical societies. There is also the human factor. Expertise depends on individuals. A master craftsman may develop exceptional methods. If those methods are not codified and transmitted effectively, they may not survive beyond his or her workshop. Archaeology reveals outcomes, not processes. We see the finished box, the drilled core, the aligned pyramid. We do not see the training sessions, the failed experiments, the iterative refinements that preceded them. The idea that knowledge could fade gradually provides a conservative explanation for why certain early achievements appear singular. It does not require hidden civilizations or extraterrestrial intervention. It requires social change. As the exploration continues, another perspective emerges. Modern experimental archaeologists have attempted to replicate many of these ancient achievements using reconstructed tools. Some have succeeded partially, others have encountered difficulties matching specific tolerances. The next layer of inquiry examines these replication efforts closely. What have modern experiments demonstrated? Where have they struggled? And what do those successes and limitations reveal about the plausibility of known methods versus the possibility of overlooked refinements? The discussion shifts from speculation about loss to hands-on attempts at reconstruction, where copper meets granite once again under controlled conditions, and the results speak quietly through dust and measured grooves. In recent decades, as debate about ancient Egyptian stoneworking has intensified, one response has been straightforward: test it. If copper tools and sand can cut granite, then build the tools, gather the sand, and attempt to reproduce the artifacts. If sledges and wet sand can move heavy blocks, then assemble a team and try. Experimental archaeology has made meaningful progress in this direction. Researchers have constructed copper saws, tubular drills, dolerite pounders, wooden sledges, and mock ramps. They have documented force measurements, wear patterns, cutting speeds, and tool degradation. These experiments have produced valuable data. They have also revealed limits. In controlled settings, copper tube drills combined with quartz sand can indeed bore holes into granite. The process works. It is slow. It requires continuous replenishment of abrasive. The copper edges wear quickly and must be reshaped. Maintaining consistent vertical alignment demands attention. When attempting to replicate some of the spiral groove patterns observed on ancient drill cores, modern experimenters have achieved similar markings. However, achieving the tightest and most uniform groove pitches reported in certain ancient examples has proven challenging in limited trials. Some experimental runs suggest that manual bow drilling produces variable advancement rates. The downward feed depends heavily on the operator's rhythm and applied pressure. Maintaining a constant descent per rotation without mechanical regulation is difficult. Researchers have attempted to increase consistency by adding weighted pressure to the drill shaft. Even so, tool wear and abrasive distribution introduce fluctuations. In some cases, drill tubes become slightly oval under stress, affecting cut uniformity. It is important to note that experimental setups often operate under constraints of time and funding. Modern researchers may conduct trials over days or weeks. Ancient workshops, by contrast, could refine techniques over years. Still, when replication attempts struggle to match certain features precisely, it raises questions about whether additional mechanical aids were used. The Serapeum boxes present another challenge. Modern teams attempting to shape large granite surfaces to near-flat tolerances using hand tools report significant time investment. Achieving consistent flatness across multi-meter surfaces requires repeated measurement and correction. Some modern machinists who have examined reported flatness measurements from certain Serapeum boxes have expressed skepticism about the ease with which such results could be obtained using only simple hand abrasion. Experimental lapping of granite slabs can achieve high flatness, but the process is labour-intensive and requires systematic checking. Without modern precision plates and marking dies, verifying flatness relies on alternative methods, such as rubbing paired surfaces together and observing wear patterns. Such techniques are plausible in antiquity, but replicating them at Serapeum scale remains demanding. Stone vase replication offers additional data. Modern artisans have carved stone vessels using copper tools and abrasives. It is possible to produce symmetrical forms and thin walls through careful grinding and polishing. However, achieving extremely uniform wall thickness through a narrow neck requires exceptional control. In some modern attempts, small deviations become apparent under scanning. The most precise ancient examples sometimes display consistency that challenges quick replication efforts. Again, this does not imply impossibility. It suggests that ancient craftsmen may have had highly refined processes not fully replicated in limited modern trials. Transportation experiments have been more conclusive. Tests using sledges on damp sand demonstrate significant friction reduction. Teams of workers can move multi-ton blocks with coordinated pulling. Modern recreations of small-scale ramp systems show feasibility for lifting stones incrementally. These successful replications support conventional explanations for block movement, though scaling them to pyramid magnitude still requires large labour forces and careful planning. Where modern experiments sometimes struggle most is not improving basic feasibility, but in matching the highest reported tolerances and efficiencies attributed to certain ancient artefacts. This distinction matters. Feasibility demonstrates that copper and sand can cut granite. It does not automatically confirm that all ancient stonework features are fully explained by the simplest reconstruction. In some cases, reported measurements from ancient artifacts are themselves debated. Critics argue that certain claims of millimetre-level precision are overstated or based on limited sampling. Accurate replication requires accurate baseline data. Modern scanning technologies are helping refine these baselines. Laser mapping and photogrammetry provide more comprehensive surface data than earlier manual measurements. Some findings reveal that ancient surfaces, while impressive, contain more irregularities than initially reported. This recalibration tempers claims of impossibility. At the same time, some replication attempts have acknowledged that ancient techniques may have included mechanical stabilizers not always incorporated into simplified experiments. For example, if a drill was mounted in a rigid wooden frame with a weighted feed system, it would likely outperform a handheld bow drill in terms of consistency. If a stone blank for a vase was mounted on a stable rotational axis supported by bearings made from hardwood or stone, symmetry would improve. Experimental archaeology sometimes prioritizes minimalism to test baseline feasibility. Ancient workshops may not have been minimalist. There is also the issue of cumulative experience. A modern researcher conducting a short-term experiment may not develop the same intuitive understanding of abrasive behaviour that an ancient craftsman developed over decades. Skill acquisition matters. However, even accounting for skill, certain features continue to prompt scrutiny. Deep saw marks on granite blocks suggest extended, steady cutting. Some groove spacing measurements imply feed rates that appear efficient relative to manual-only operation. When replication efforts fail to reproduce specific characteristics within reasonable timeframes, it invites reconsideration of tool setups rather than abandonment of conventional material explanations. It is also possible that some ancient artifacts represent exceptional craftsmanship rather than typical output. Outliers in skill can exist in any era. Modern machinists sometimes achieve results that exceed standard shop tolerances due to individual expertise. What modern experiments ultimately demonstrate is that ancient Egyptian stoneworking is neither magical nor trivial. It occupies a space where basic materials, copper, sand, stone, are combined with organisation, measurement and persistence to achieve outcomes that can be replicated in principle, but not always easily. Failure to replicate quickly does not equal evidence of lost high technology. It indicates that the combination of method, time and mechanical setup may not yet be fully reconstructed. As the inquiry continues, another question emerges naturally. If certain techniques were refined and perhaps specialised, why did ancient builders leave behind no clear, preserved machines or detailed depictions of complex mechanical systems? The next layer of examination considers why the archaeological record is rich in finished stone but sparse in surviving apparatus. Why stone persists as silent testimony, while the tools that shaped it remain largely inferred rather than found. Stone endures, wood does not. Rope frays, leather cracks, metal corrodes, and is melted down for reuse. This imbalance shapes the archaeological record more than we often acknowledge. When we walk through ancient sites today, we see the durable results of past labour. We do not see the scaffolding that surrounded them, the frames that supported them, the tool racks that lined the workshops, or the sledges worn smooth by years of hauling. If refined mechanical systems were used in shaping granite or aligning massive blocks, why do we not find clear remnants of those systems? The first and most straightforward answer is material survival. Ancient Egyptian construction sites were dominated by limestone and granite because those were the materials meant to last. Wooden infrastructure was functional, not eternal. It was reused, repaired, repurposed, and eventually discarded. In a dry climate, some wood can survive under exceptional conditions, but exposed construction equipment rarely does. Copper tools, when worn down, would have been collected and resmelted. Metal was valuable. A bent drill tube was not discarded permanently. It was melted and reforged. If specialised components existed, they likely returned to furnaces once their usefulness ended. Rope, critical for sledges and lifting systems, decays rapidly. The fibres that once transmitted enormous force across the plateau would leave little trace after millennia. Even large wooden beams used in ramp systems or lifting frames would have been dismantled once construction ended. Timber was a precious resource in Egypt. It was not abandoned casually. Imported cedar and acacia were reused whenever possible. Archaeology, therefore, preserves outcomes more readily than processes. There is also the issue of documentation. Ancient Egyptian art is stylized. Relief carvings depict symbolic scenes rather than technical diagrams. When workers are shown moving statues, the emphasis is on coordination and scale, not on the precise mechanical configuration of the sled beneath the load. Depictions are schematic. They communicate activity, not engineering blueprints. The absence of complex machine illustrations does not necessarily imply absence of mechanical systems. It reflects artistic conventions and cultural priorities. Another factor is spatial context. Workshops where tools were built and maintained may not have been located directly within pyramid complexes. Temporary construction areas would leave fewer durable traces. Once a project concluded, those areas could be cleared or repurposed. Even in modern cities, temporary construction equipment often disappears without leaving permanent evidence beyond foundations and finished structures. It is also possible that mechanical aids were simple enough not to appear extraordinary to contemporaries. A weighted drill frame built from wood and stone would not have been considered revolutionary. It would have been a practical extension of existing tools. Such devices might not merit inscription in royal records. They would be regarded as means, not ends. There is a tendency to equate technological trace with metallic complexity. We expect gears, bearings, hardened steel components, but ancient technology operated within a different material framework. A wooden A-frame, a rope and weight feed system, a guided sled platform. These can be effective without leaving enduring archaeological footprints. One must also consider scale. The number of drill rigs or shaping frames required at any given time may have been limited. A handful of specialized devices could serve an entire workshop. After completion of a project, those devices might be dismantled and reconfigured for other tasks. Additionally, some physical evidence of construction techniques may still lie buried or misidentified. Excavation is selective and incomplete. Vast portions of ancient Egypt remain unexcavated. Even when wooden elements survive, they are often fragmentary. Identifying a fragment as part of a complex machine rather than a generic support beam can be difficult without contextual clarity. The concept of preservation bias extends beyond materials. It shapes interpretation. Stone artifacts receive focused study because they are prominent and intact. Subtle traces of mechanical systems may be overlooked if they do not fit existing categories. Still, caution is necessary. The absence of clear machine remnants does limit the strength of claims about sophisticated mechanical systems. Plausibility does not equal proof. The most conservative position recognizes that known tools, copper implements, stone pounders, sledges, can account for much of what we observe, especially when combined with organized labor and time. The open question concerns refinement. Did ancient builders enhance these tools with mechanical stabilizers and feed systems more advanced than commonly depicted? The archaeological record does not definitively confirm such enhancements, but it does not conclusively exclude them either. There is also the broader cultural dimension. Ancient Egyptian architecture prioritized permanence in monuments, not in tools. The tools were means to serve eternal structures. It is not surprising that the structures survived while the means did not. When examining other ancient civilizations, similar patterns emerge. Greek temples stand in marble. The cranes used to lift their blocks are gone. Roman aqueducts span valleys. The scaffolding that erected them has vanished. In each case, historians reconstruct likely machinery from indirect evidence, cut marks, lifting holes, clamp slots, and structural features. At Giza, lifting notches and quarry marks provide hints about movement methods. Drill cores reveal rotational cutting. Saw marks trace linear abrasion. These are traces of process, even if the process itself is not preserved intact. The absence of explicit mechanical relics leaves room for interpretation, but does not automatically elevate mystery to impossibility. As this exploration approaches its final reflection, the question shifts subtly. Whether ancient Egyptian stoneworking relied on lost machines or highly refined manual methods, the physical artifacts remain. Granite boxes still sit beneath Saqqara. Spiral grooves still wrap around drill cores. Thin-walled vases still balance delicately behind glass. The enduring reality is not that technology was inexplicable, but that it was effective. And as attention moves toward a final quiet consideration, the focus turns from how these achievements were accomplished to what they represent. A civilization's determination to shape stone with intention, leaving behind structures and objects that continue to invite careful study long after the hands that made them have returned to dust. The desert does not keep everything. It keeps what resists it. Wood collapses back into the ground. Rope loosens into fibers and disappears. Leather stiffens, cracks, and returns to dust. Metal corrodes, or is melted down and reborn as something else. Even memory thins when it is not repeated. Names fade. Techniques soften at the edges. Workshops empty. Tools are repurposed. Hands that once knew exactly how much pressure to apply to granite grow still. And yet, the stone remains. A granite box beneath Saqqara still sits with its lid aligned carefully across its rim. A drill core still carries the spiral path of rotation along its surface. A vase carved from diorite still curves inward with walls thinner than instinct expects. The Great Pyramid still stands square to the cardinal directions. The Sphinx still faces east. Whatever methods were used, whatever mechanical aids may have existed, whatever refinements were perfected and then quietly set aside, the result endured. Perhaps that is the real measure of ancient Egyptian technology. Not whether it exceeded our expectations, not whether it concealed hidden machines, not whether every tolerance can be matched quickly in a modern laboratory, but whether it achieved what it set out to do. The pyramids were meant to endure. They endure. The chambers were meant to hold weight. They still hold it. The vessels were meant to be symmetrical, balanced, precise. They still are. It is possible that certain techniques were gradually forgotten as political priorities shifted. It is possible that specialized workshop knowledge narrowed and dispersed. It is possible that mechanical refinements were never written down because they were understood too deeply to need explanation. Knowledge does not always vanish in fire. Sometimes it simply loses context. A method perfected for shaping granite beams might not survive when no more granite beams are required. A specific approach to drilling might fade when fashion changes. The quiet attrition of skill can occur without drama, but the stone does not forget the hands that shaped it. Each groove in a drill core is a record of rotation and pressure. Each flat granite surface is a record of abrasion and patience. Each aligned foundation is a record of careful sighting against the horizon. These are not abstract symbols. They are physical traces. When we look at the Giza Plateau, we are not looking at mystery in the sense of impossibility. We are looking at durability. We are looking at a civilization that invested extraordinary effort into materials that would outlast the people who handled them. In that sense, the question of unexplained technology becomes less about lost secrets and more about enduring intention. The ancient Egyptians understood something simple and profound. If you want something to survive you, you build it in stone. They built in stone not only because it was available, but because it resisted time. Their monuments were not temporary shelters. They were statements of permanence, and permanence carries its own kind of silence. The texts tell us about gods, kings, rituals, and offerings. They do not describe every tool. The machines, if they existed in refined form, were built from materials that yielded to decay. But the stone carries forward the final expression of those processes. Perhaps that is enough. In the quiet of night, when the world is still, it is possible to imagine the plateau long before tourists and scaffolding. Workers moving in rhythm, the steady scrape of abrasive against granite, the low murmur of coordination as sledges inch forward, the careful checking of alignment under the open sky. No electricity, no engines, no spectacle, only method, only persistence, only the decision to shape something so precisely that it would still invite examination thousands of years later. What endures after knowledge fades is not the diagram, it is the result. And the result is still there, rising from limestone bedrock, holding its angles against wind and time, quietly reminding anyone who studies it that human hands, guided by discipline and belief, once moved mountains of stone into deliberate form. The mystery is not that they did it. The mystery is that they did it so well that we are still measuring it, still testing it, still asking how. And as the desert cools and the stars settle above the plateau, the stone remains exactly where it was placed, patient and unchanged, long after the voices that built it have fallen silent.